All right, so like I said, you guys were on to Unit 2, manual transmission transaxle. I did make a change. In the past, we covered manual transmission, and then we covered manual transaxle completely separate. But I realize it's a bit redundant. If you can understand the transmission, you're about 90% there from understanding the transaxle. All we need to add in is it just has a slightly different arrangement of the shafts and then the differential part. And in the transaxle, having the differential is not a real big deal, especially because we covered differentials separately, which is coming up. So we're rolling a couple things together. And first, why do we even need the transmission? So we've covered this just a bit, but if we were to have, a light vehicle and only flat roads, and we didn't really need to accelerate quickly, we probably could get away with no transmission. If we were to just not put a big demand for torque on the engine, no problem. But unfortunately, these vehicles are bigger and bigger and heavier, and the customers want them to accelerate quicker and quicker. So we really need a transmission so that we can take the engine torque, which is limited, and increase it to the amount that we want. Basically, that's really why we do it. So let's say in first gear, um, you came up to a hill, you'd expect it to be able to accelerate this Tacoma, a reasonable with a reasonable amount of speed and acceleration. The engineers will come up with a gear ratio, do a calculation, and determine what gear ratio they want to make the vehicle feel how they want it to feel. So, at least from a pure standpoint, the transmission is designed for the vehicle, right? We don't we don't necessarily just make a transmission and then it fits all the models we have. If we let's say they designed the new Tacoma, we can't really use bigger trucks. Bigger trucks, like a full size truck, is typically not going to come in a manual transmission option anymore, although they used to. They would design that transmission to give basically to match that vehicle's weight, but also to match that engine's torque, right? So if you have, let's say, an older four-cylinder Tacoma, they had a lot of gear reduction in first gear because they had like a kind of a kind of a weak four-cylinder back in the day. The 22R, the infamous, right? They don't, that's a great engine because it lasts a long time, but that is not a powerful engine, right? So we can manipulate the engine's torque and multiply it. Now, if you were to look at, let's say, a Dodge Ram diesel, so it'd be the Cummins diesel, that actually would need a totally different gear ratio. The diesel has a ton of torque. So if it has a ton of torque, we don't really need to do so much gear reduction. And that would, you know, be great. The kind of the issue is if you have the Cummins diesel in a manual transmission, it's probably like a 2500 or a 3500, which means you're going to want to tow. So if you're going to want to tow, let's say this is a boat ramp and you're towing your big boat out of the water, actually you do need a ton of torque, an amount of torque that probably that Toyota could never produce. So they have a very aggressive gear ratio for first. But what's kind of interesting is if you're just driving the truck, you might start off in second normally, but if you were to get on the boat ramp, you might start off in first. So it's it's kind of interesting. Really, the transmission should just make the engine move the vehicle the way we want or tow the things we want, right? So that's going to be a common theme here. Now, if we were to discuss how we come up with gear ratios, well, it's a pretty simple calculation. If you look at these gears, first off, the input is the small brown gear. The output is the silver gear. So we're going to do the calculation driven divided by drive. So so in a way, it's really like driven gear is the output gear, drive gear is the input gear. So you do driven divided by drive. That means the output divided by the input. If you were to look at first gear in that example, that Tacoma, if we had 36 teeth on the driven gear and then 9 teeth on the drive, you could literally just count the teeth up They all look the same, so you might need to make a mark on them and then count them up. But you do 36 divided by 9, you'd come up with a 4. That would be a 4-to-1 ratio. That would mean your engine will turn 4 times before your output shaft to your transmission turns 1 time. And so who remembers a little bit like what would be the benefit there? Engine turns 4, transmission output turns 1.
Extra torque.
Yeah, 4 times the torque. But in in life in physics is no different. You don't get anything for free. So if you've got 4 times the torque, what did you just sacrifice?
The speed.
Definitely. So now you have 1/4 the speed, right? So in first gear, that's great. We don't need a lot of speed in fourth. We just need a lot of torque to get the vehicle moving. And so yesterday, Roberto made a pretty interesting point. He's heard people, people he knows at his job and places say, "Oh yeah, yeah, you don't downshift into first gear unless you're stopped." And part of the reason is first gear is a 4-to-1 ratio. So like if you're anything other than stopped, you probably don't need a 4-to-1 ratio. But that's only true for some transmissions. Every transmission could be a little bit different. So if you were to look at this, you would figure this this output is going to be turning one speed. This input is going to be turning a different speed to go from second, which is a 3-to-1, down to first, which is a 4-to-1, and sometimes it's even more of a distance. Sometimes it's more of a speed difference. The bigger the speed difference, the harder it is to get those gears to turn the same speed, so you can couple to them, and therefore select that gear, right? So going down into first in the Integra, that's going to be, there's going to be some harshness there. That's a big gear change. Sometimes you're even going to try to move the shifter and it's going to be hard to get it into gear. But if you're stopped, it'll go right into first, no problem. Or if you're almost stopped, because you're already going slow enough, that gear is not going to be spinning all that fast. You can couple to that fairly easily. So this is something to keep in mind as we continue. You'll notice the speed difference between like fifth and fourth there's not that big of a difference. First, second, and third are actually pretty equally split in this case, but they're not always. And so here we are. Let's say that we're in first. We get our 4 times the torque at 1/4 the speed. But like we were saying, first gear would only be for very, very low speeds. So that's fine. We don't really need to go fast in first. Then when we get the speed up a little bit, the RPMs are up, and you're sort of like, okay, I need more speed, but I'm out of RPMs. My RPMs are getting closer to red line. That's when we'd let go of that first and we grab that second. Second gear has 27 teeth on the output gear and 9 teeth on the input gear. So again, the formula is driven divided by drive. 27 divided by 9 equals 3. So you get a 3-to-1 ratio. So you had 4-to-1, 4 times the torque, 1/4 the speed. Now you get 3 times the torque, which is still great. Second gear still. That's why some people will just start off in second. Would I do that on Tegra? No. Would I do that on that Ram with the diesel? If I had no weight that I was towing, I probably would. Second gear will pull it right out of the hole, as they say. And then you can see, and and I want to point something out. You don't just do the big number divided by the little number, okay? Just want to make a point right there. You don't simply just look at the two numbers and automatically do 27 divided by 9, 36 divided by 9, etc. Okay, you got to actually put them in the formula of driven divided by drive. Cool? So there you go. You're pretty happy with second, but you need some more speed because your RPMs are up. Your vehicle's then moving. Remember, like as your vehicle's moving, it takes a lot less force to keep it moving. It takes a lot more force to get it moving. That's why first has to be, 4-to-1 or sometimes more. Sometimes first is a little closer to 5-to-1, actually. Right. Then we go ahead and we'll grab third. 18 divided by 9, that's easy math. That's a half. That's 2-to-1. Right, 9 is a half of 18. So a 2-to-1 ratio, the 18 divided by 9, there you go, 2-to-1. Everything's, you're getting up, moving a little bit quicker. Something really cool happens in fourth, and in a manual transmission, it typically is fourth. If it's a 5-speed or a 6-speed, fourth gear is this is pretty standard. Look at that. What happened in fourth? You guys tell me. Dang it.
Is
Fourth
one
gear.
to one.
Bingo. So in the 1-to-1, that's when your engine turns once and your output shaft, your transmission turns once. So when we're talking about the transmission, it's all about what you put in versus what you get out. So if you turn your input shaft once and your output shaft turns once, that's in 1-to-1. And I was showing you on the transmission a couple people yesterday. On the transmission, it's very easy to locate fourth because fourth gear couples the input shaft to the output shaft. And you're like, oh, okay. So if you start with fourth as the baseline when you're trying to identify what gear's what, it makes it much easier, right? Because when you move your shifter, this is going to be my shifter for the day. I got blue shift knob. When you go into fourth, it's back here, right? So if this is the front of the car, you go fourth gear pulls back, but in reality, the bottom goes forward. So you'd find the sleeve that you can tell couples the input to the output, and you can even turn the shaft and be like, oh, I turned the shaft once on the input, once comes out on the output. They're 1-to-1. They're the same speed. Cool. Then once you know that fourth is there, that would mean that same sleeve, because right, the H pattern, first, second, third, and fourth, that sleeve would be third, right? When you're in that gate, right, the 3-4 gate, it's the fork moving the one sleeve. Fourth is back, which is really forward in the transmission. Third would be forward on the shifter, which would really be back in the transmission. Boom, you locate that sleeve and you're like, all right, cool. Right there. That's fourth and third, fourth and third, fourth and third. Right. And then you know that the one behind that is going to be first and second. Remember, first is forward, so it moves the sleeve backwards. And second is pull the shifter back, burn. That's going to slide the sleeve forward. Okay. So there's understanding everything kind of starts with fourth gear when you're trying to locate these gears. That's what I would do. Additionally, another point is if for whatever reason you're trying to measure the torque output of the engine, you'd need to put it in direct drive, which would be fourth. So if you see, these dyno pulls and boom, 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 it's in fourth. In a manual, it needs to be in fourth. That's the 1-to-1. When they dyno test an automatic, it also needs to be in direct drive. I just don't know what gear that is, and they got to command it into that gear, and then the torque converter is doing its thing, and so they don't. The automatic's a little bit trickier because you have the torque converter doing its thing, so it's harder to measure the engine torque. I guess it's more relevant to measure wheel torque anyway, but you'd be getting artificially inflated numbers if you did it in a 2-to-1, like in third or so. Cool. Now, then fifth gear, in this case, something very unique happens. We go with, remember, the calculation is driven, drive, driven, drive, driven, drive, driven, drive. Driven is 6. Drive is 9. What the heck? See how now you see you can't just do the big number divided by the little number. In this case, it's opposite. It's the little number divided by the big number because it's driven divided by drive. 6 divided by 9, that's a little bit difficult for me to do, but we've done it already. It's 0.66, and I think it keeps going. So it's a horrible gear ratio if you ask me. It might be 667. Let's call it 667 to 1, because 667 is probably rounded up from what it really came from. All right, what the heck is going on here? 0.66. It was 4-to-1, 3-to-1, 2-to-1, 1-to-1, and now it's 0.6-to-1. Tell me. Somebody knows. Does anybody know?
The overdrive.
Yeah, exactly. We got our overdrive right there. So when you're in fourth, you're at true 1-to-1, right? If you got 2,000 RPMs in, you got 2,000 RPMs of the output shaft out. You're in direct drive. When you go into fifth, the whole purpose of fifth is to drop your engine RPMs. That's your overdrive. You're overdriving your transmission. Your transmission, you're putting in one and you're getting out more than one at the output shaft. It's being overdriven. Cool. Mainly for fuel economy and emissions. But I gotta say, this one I appreciate. If if we were to just look at a car that's been around for a long time and had a lot of transmissions, we would go with logically the Camaro. I should have pulled the Camaro over that way. I could have had it match. Instead, I still got this junky Jeep. Um, the Camaro started 67. If you wanted a manual, you got the 4 speed. There were cars before that that were actually 3 speeds, and the 3 speeds were typically like an underdrive, a direct drive. But the 4 speed was traditional, it was classic. It was just the first, maybe 4-1, second, maybe 3-1, third, maybe 2-1, and then fourth, 1-1. And that was it. That was as high as you got. And at the time, I mean, there's something to really love about that 4 speed. Basic, you're in the zone. Um, just even just looking at the shifter, it just has the H. It's just the H pattern. First, second, third, fourth. It's pretty cool. But when they made that 67, 68, 69 in these years, they didn't really care about fuel economy quite yet. They started to, but in the late 60s, it was like, I don't know. If, for us in our lifetime, it was a little similar to, I don't know, what would it be around like 2019, 2020. Gas was cheap. I still remember gas was cheap. And so it was like, whatever, punch it. Who cares? Gas was really cheap. We didn't really care about saving gas. And these cars, and they didn't really go that fast either. They were quick off the line. They had a lot of power, but you weren't really looking to cruise probably very regularly at 80. Now, especially here in California, you guys jump on the freeway, you're pretty close to 80. You're just cruising at 80. Like for me, it might be a bit over 80, but that's when I'm on my way home, I'm hammering at 80 miles an hour for an hour and just, my motorcycle's zinging at like 6,500 RPMs. It doesn't care, but you know, that's not ideal. It's kind of loud. It's not good on gas. It's probably not even really great for the engine to be turning that fast, but in my bike, that's all I got. It'd be pretty cool if they'd add some gears to motorcycles, but they don't. So if you look at that 4 speed, it was fine for the time. And then, we had a lot of oil issues in the 70s, and then, a lot of times that's when we started bringing in the emission standards, especially in the mid to late 70s. And next thing you know, it's 1982, and if you want to buy a Camaro, it comes with a 5 speed. So in the 5 speed, fourth gear is still direct drive, but in the effort to save gas and in the effort to lower emissions, they add fifth. So that's just like this right here. You get your overdrive, and the purpose of overdrive was not to make the car go faster. The purpose of overdrive was to drop the engine RPMs when you're going the same speed as you were in the 4 speed. So if you want to be able to cruise at 80 like me, in that 4 speed, that engine's gonna be wound out. So that's the thing. I really like those older cars. The older Camaro, like a 67, it's got a good figure, you would say. I like the body lines. I absolutely like the shape of the car, but I'm spoiled by modern times. I would not I would not be able to keep that car a carbureted, small block and a 4 speed. That thing, I would end up finding a modern Camaro and I'd yank the whole powertrain out of it and I'd do like a full fuel injections one subject, but even for the transmission, I would want a 6 speed. So you got into the more modern years, right? So the 80 something Camaro was a 5 speed, and then if you got and that's true for some of the cars that you guys would be into, even the Japanese stuff, right? 1990 something, so 5 speed. But by the time you get into the late 90s, a lot of times you're looking at a 6 speed. You get a 6 speed. The sixth is just another overdrive. So like on this one, we had a 0.66 to 1. The sixth might be like a 0.50 to 1. That's a way to drop your RPMs even lower and to increase your emissions even a little, decrease your emissions even a little bit more. And so the transmissions have evolved really no different than automatics. Automatics have gone from 3 speeds to 4 speeds to fives to six to eights to tens. And the manual has really gone from like 3 to 4 to 5 to 6. And then for the most part, six is where they land. Some vehicles have a seven. I don't really see any other manuals having much more than that, unless you get into the bigger trucks, which is basically it'll be like a 6 speed with a splitter. So you put the splitter on reduction, and then you'd have your first six, and then you could move the splitter to one, and you have your second six. And then, I don't exactly know all the gears that they would have, but at a minimum, you just had 12. Even though it's a 6 speed transmission, there's a there's a way to reduce the gear ratio going into the transmission, so it ends up giving you a whole nother six ranges, six different gear ratios. Sometimes they have a three settings. It'd be like super reduced, less reduced, and 1 to 1. And then you still have the six, and the six. You can get 18 speeds out of that. But generally, for automotive purposes, the transmissions mostly stopped at 6 speeds. And that's why we got there. So this is just kind of showing you how you'd get the benefit if you had 18 by 9 driven divided by drive. What are your thoughts? You come in with 100 foot-pounds on A. That means you got that 22R. It's got 100 foot-pounds. If you got 100 foot-pounds on this, what are you gonna make on A? What are you gonna make on B? You should be able to know that number. It's also on the screen. Driven divided by drive is, oh, it's 2 to 1. So what do you do to your torque? You double it. You double it, oh, you get 200. There you go. Here's your 200 foot-pounds. Cool. So that's the mathematical calculation. Like in electrical, Ohm's law, you can calculate a lot of stuff. Do we do it as technicians? Not really. We don't probably run the numbers, but do you need to understand why the numbers are what they are? Yeah, that's about it. That's why first gear being a 4 to 1 will give you 4 times the torque, right? There's 4 times the number of teeth on the driven compared to the drive. Cool. And by the way, in this case, this was simplified almost like a bicycle, like a mountain bike, like a 10 speed. The front sprocket stayed the same, and the rear sprocket, you got a big gear, or you can derail the chain and get a smaller gear, derail the chain and get a smaller gear, derail the chain and get a smaller gear, derail the chain and get a smallest gear. That's how like a bicycle works. In reality, in the transmission, the driven and the drive will use different gears every time. Like in this one, they showed you using the same drive gear each time. In the transmission, it's not really the case, right? We have a different gears and arrangement. All right, so we'll get to that. Now, what types of gears? Okay, I got some options for you. This is basic gears and bearings coming up here. So a spur gear, that's like you ever seen the cowboy walking around and they got the little spurs on the back of the boot? You know what those are for, by the way. It's not just for show. Those get the horse moving. Those spurs are it's kind of like a star, right? A star, and these sort of look like spurs. They come straight out, right? These gears are straight out. So when these gears are coming together, they're coming straight into mesh. The cool thing is, they're strong. The negative thing is they tend to be loud. They're coming into mesh and coming out of mesh, and they're like just hitting each other right face on, face on, face on, face on. Um, Another side benefit is they don't cause any thrust forces because the gears are straight. The teeth are straight on. We typically use a gear like this on some vehicles in reverse, specifically a Honda. You ever heard a Honda get put in reverse and back up? What do you hear? Let me make the sound.
Obnoxious revving noises.
Yeah, you'll hear the revving, but if they had a stock muffler, you'd still hear these spur gears in reverse. It's kind of like they sing. They sound like a supercharger kind of, So that's the reason why in reverse on those they're kind of noisy. Reverse is just a straight. They'll call it straight cut gear. I almost used the slang right there and forgot to tell you the slang. Spur gear is like a straight cut gear. It's straight cut. It's good. It's cheap. It's just loud. But in reverse, nobody cares. In fifth gear on a 5-speed Honda Civic, what'd you say? Huh? You know, so you can't have a transmission making all that screaming. They need to be able to listen to the radio and also hear their loud exhaust and things like that. So the straight cut gears are good. They're simpler to machine. It's easier to manufacture these. But the negative would be sound. So you don't really see the straight cut gears used often, except for maybe reverse. And a lot of transmissions don't use them in reverse either. If you noticed, a couple people worked on some transmissions. A lot of the transmissions we're going to see don't have any spur gears like that, but they could in reverse. And then a helical gear is kind of like a straight cut gear, except they cut it at an angle if you look right there. And then, of course, this angle has to match this angle. And the way that they come together, they you're almost like slowly leading the face of the tooth into the other face of the tooth. So rather than right face on, it's sort of like, hey, we're gonna mesh these. That makes it nicer and a lot quieter. And actually, these can be just as strong. Some would even say, maybe stronger, because you get actually more. The gear has more length, which means you can spread the surface area across that greater length. But there's there's one negative. These are more difficult to manufacture, so they cost more. The other thing is they generate for the first time this axial thrust force. So this gear and this gear riding together try to push this gear to the right and this gear to the left, which isn't horrible. But when we get into bearings in the next slide, you have to know that we have to deal with that. So any force that's on the vehicle, we need to have that under our control, and we're going to use different types of bearings. So with these gears, we're really worried about the shaft up and down and left and right, right? That's like a radial force right here. With this one, we still have those forces, but we also add this axial. So now we have to have a bearing that's going to take this. If this axis were to move like this, we have to have a bearing that's going to withstand that amount of force that's generated by the helical gears. And there's another type of gear, mostly we talk about in differentials hypoid, but we'll cover that when we cover differentials. Transmissions generally don't use a hypoid gear, a little bit different. So like we were saying, bearings. This bearing really has very, very limited ability to handle an axial force. It's good at a radial force. You can see like an up and down in here. If you had a gear spinning on this, it would be great for this bearing. If you were trying to get this bearing to hold an axle from moving like this, that axle is going to basically move and blow out these little pins. The pins are going to try to move sideways. There's not a lot of side surface on these. They'd end up banging into this little race and they'd end up failing, right? So this bearing is not going to work well for axial forces. Now, luckily, we don't need this bearing for axial forces, so it's fine. And then you got the split needle bearing, which is essentially the same as a needle bearing, except when we assemble the transmission main shaft, we don't have a real good way to always slide the bearings into place. Like sometimes there will be a boss or a built-in gear on the shaft, and you couldn't get the bearing over the gear. So instead, we use a split bearing, and it goes around the gear and then comes on as in a split. These do the same job right here. We use these a lot on speed gears. So first, second, third, fourth, at least first, second, third. And then the most simple type of bearing would actually not be a bearing at all. It'd be a bushing, but it's still classified as a bearing because it's like load bearing. It bears the force. The reason it's not exactly a bearing is if you look, there's no rolling elements, there's no inner and outer race. It's just like a solid slug. It's a piece of brass, it's a piece of bronze, these types of things. So like a pilot bushing, we talked a lot about the pilot bushing. That'd be your bushing. We do use bushings in manual a lot of times for maybe like an output shaft or maybe not even output shaft. Maybe if we have a shaft that's going to be spinning but not necessarily generating a ton of force, and we know we can have it well lubricated, a bushing would be fine. I have to think about where we're going to find a bushing in a manual. In an automatic, it's easy. The torque converter rides on a bushing that's pressed into the pump. So we do use some bushings, and a lot of times the slip yoke, that's where you'd find it in the manual. If it's got a slip yoke, it'll have a bushing right back there for the drive shaft slip yoke. And then a roller bearing, if you look, these roller bearings, you'll see it's more like a cylinder shape. So these rollers are really good for that radial force, but axial not so much, right? This flat edge hitting on that flat edge of the race is not, it might be able to handle a little more radial force or a little more axial force than this because you can see it's got a little more surface area there, but it's not, that's not the bearing for an axial load. What would work better is actually a ball bearing. The ball bearing, because it's round, and if you look, it's got an inner race right here that's got a semicircle and an outer race that's got a semicircle. So they're great for that radial up and down load, but side to side, they're a little better because you have a little more surface area here. So this ball bearing is a little stronger in this direction, and it can also, because the semicircle race, have a little bit of a surface area right there to contact against. So ball bearings can be decent um, for axial loads, but there's one that's superior, and it actually wasn't a part of this one. But when we get to it, it's the tapered roller bearing. When we get to it, I'm going to point it out. So just remember these. And then we get to tapered roller bearing. We're going to talk about it. It is superior for the axial loads, but it comes with a negative. It's only superior in one direction. So if you don't have a ton of axial loads, the ball bearing's perfect, run it. If you really have a lot and you need to upgrade to a tapered roller bearing that sits like this, cool. You need another one to sit like that. So that way they can control it in both directions. And we do use those in some transmissions, and I'm going to show it to you. All right, cool. So how those apply to the manual. If you look here, all the components, we're going to have an input shaft bearing right here. If you notice, it's a ball bearing. We're going to have several different speed gears, fourth, third, second, first. Those will all be sitting on most likely split needle bearings. The output shaft will have a type of bearing, but I don't see it. Out there you go. That's a roller bearing right there. And then the counter shaft is going to have its own sets of bearings. Looks like we've got a roller bearing, another roller bearing, and another ball bearing back here. So kind of the point being, there's a whole bunch of bearings in this transmission. So when we start talking about transmission rebuilds and overhauls on an automatic, that was like, really talking about, we need clutches and steels. On a manual, we don't have clutches and steels. We have a clutch that's external. That's not even an overhaul. That's a clutch replacement. But inside the manual, we're more looking at bearings. So if you had a manual transmission noise and you wanted to go in and quote unquote rebuild it, you're going to replace all these bearings. It's a pretty inexpensive part, you know, cost, but the labor can be a little bit intense. Um, but for the ASE, you really need to know what bearing would be making the noise. So when we get into this, you need to know what is turning and when it's turning. So like, for example, the input shaft looks like it goes all the way through, but it doesn't. The input shaft more like has the clutch disc splined to it. That actually ends right here. And then your output shaft sits right behind it, but these are not connected. So this one can turn separately from this one. And there's certain things we can do to determine if the noise is on the input shaft versus the output shaft. And additionally, our input shaft is driving our counter shaft. The reason it's counter is it turns the other way, counterclockwise. It turns counter direction. That one is a little tricky because it's driven by the input shaft. So if the input shaft is turning, it is turning the counter shaft. There's no way to get the counter shaft to stop. But depending on what gear you're in, you can vary the amount of force, the amount of the load per se on the bearings. So like remember with wheel bearings, if we think we have a bad left front wheel bearing, we'd get up to speed in the vehicle and we'd sway the vehicle to the right. And that would put load on that left bearing. And if it got louder, you'd be like, oh, I think it's that left bearing. Then if you turned left, it would take the weight off of that left bearing. And if it got quieter, you'd be pretty sure it was that left bearing, right? So on a road test, we can do different things to, for the most part, know what bearing in here is bad if it is a bearing. Okay, so like just as a basic example, if you depress your clutch pedal, that means your clutch pedal's down. You guys should all know the clutch disc stops. If the clutch disc is splined to the input shaft and the clutch disc stops, what does the input shaft do? It's going to be a good question for you. You depress the clutch pedal, the clutch disc stops. The clutch disc is splined to the input shaft stops. So if you had an input shaft bearing right here, this ball bearing, and it was messed up, what could you do to determine if it's that bearing or not?
See if the noise goes away when you engage the or disengage the clutch.
Bingo. It's that simple. Now, if I was on the ASE panel of people writing questions, we'd say, oh, yeah, that's how that input shaft bearing works. So what if we say a vehicle comes in for a bearing noise, whatever, but when the clutch pedal's up, it makes it, and when the clutch pedal's down, it goes away. Yeah, 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 that's brilliant. That could be that input shaft bearing, right? So your job is to know what turns, what doesn't turn, and how do you make something turn, and how do you make something not turn generally, right? So that was a good example of the input shaft bearing. But what's interesting is it gets a little more complicated than that because your input shaft is turning when you engage the clutch. So if the clutch is engaged and the input shaft is turning, technically this is the problem. The input shaft bearing is turning, yes, but it also turns the counter shaft. So if you had a loud bearing back here, you could probably hear it when you let the clutch pedal up too. But the next step you may want to do is let's say you jump out and you get on a road test, right? And in first gear, we're going to cover power flow in a second here, but in first gear, the input shaft turns the counter shaft. It does not turn the output shaft. Okay, right there, you see a gap right there. That's on purpose. Input shaft turns the counter shaft. First gear is right here. This counter shaft, all these gears are fixed. All these gears are going to turn with the counter shaft, and all these green gears are going to turn a corresponding red gear, right? So you'll see all these gears are spinning, but none of them are necessarily attached to the actual output shaft. Okay, so in first, when you select first, you attach first, you couple it to a hub, and now first gear grabs a hold of the output shaft and it makes the output shaft turn at the first gear speed, right? So power comes in, goes through this bearing, goes down to the counter shaft, which all spins and it goes through all their bearings. But then the counter shaft first gear, it always was, but it's continues to be splined to the first gear speed gear, which is now splined to the output shaft, which now makes the output shaft turn at the first gear ratio. So let's just say we thought it was an output shaft bearing. That output shaft speed would change the pitch of that bearing. So if it was like Well, if I'm stopped and I let my clutch pedal out and it makes the noise, I'm explaining to you this output shaft is not turning at 0 miles an hour. So it can't be that output shaft bearing. If the speed comes in only as you're moving, then it'd be like, oh, okay, I get it now. If it's when I'm moving with vehicle speed, it would probably more be like an output shaft bearing. Yes. Makes sense. Now let's go back to what was happening in first gear. The torque is going through the input shaft, and then the torque is being passed. A lot of torque, by the way, is being passed through the counter shaft. If we had an issue on the counter shaft, we'd hear it right there too. So it'd be a little hard to tell if it's the input shaft bearing or the counter shaft, right? And then similar in second, power comes into the input shaft, transfers to the counter shaft, goes up through second, boom. Third, input shaft to counter shaft, goes up to the output shaft. Fourth is where the magic happens. In fourth gear, we couple the input shaft to the output shaft directly. The counter shaft still spins though. Okay, so counter shaft still spins. But if the torque is coming in the input shaft coupled directly to the output shaft, because fourth gear is here, what's the counter shaft doing? It's spinning, but is it carrying in any torque? Is there a lot of torque being passed through?
Is torque reduced?
Torque in fourth would be 1 to 1. My point is, if we're trying to test a bearing on the counter shaft, if you put it in fourth, the counter shaft is no longer taking any torque. So it's sort of like, remember we had that left front wheel bearing that was bad? If you take the weight off the left front wheel bearing and it gets quiet, it's because it was the left front wheel bearing. Makes sense? We just took the force or the load off of the counter shaft, and if it got quiet in fourth, it's a counter shaft. I don't which bearing, I don't know. Maybe it's this bearing or maybe it's this bearing or something, but we know realistically it's a counter shaft bearing issue because it's quiet in fourth. Makes sense. So if I was on the ASE panel, I'd say something along the lines of a vehicle comes in with a bearing noise and it's loud in first, loud in second, loud in third, but it gets quiet in fourth, and then it comes back and gets louder in fifth. Boom, that's a counter shaft. Take it. You can take it to the bank. Make sense? What bearing? I don't know. And ASC doesn't know either. They just know it's a bearing that's on the counter shaft. So when you take this transmission apart, you're like, let me hone right in on that counter shaft bearing. Because on the ASC, we're not just trying to replace every bearing when we have every bearing noise. We're trying to know what bearing it is. So when we get in there, we can just replace the bearing it really needs, even though labor costs are high. So you might end up saying, hey, might be a good time to do all the bearings. You still really need to be able to know what bearing you're going after. Cool. And so these are the types of things we get into. That's a little bit of a way to tell if it's an input shaft versus a counter shaft. The output shaft, again, that has nothing to do with engine RPM. That's all with vehicle speed. This gets the slip yoke and that turns the drive shaft. So that's a vehicle speed. You could tell a lot about the nature of the issue just based on knowing what gears turn and which bearings carry the force, depending on the gear, depending on the conditions. Cool, makes sense. So we talked quite a bit last week about clutches, and you can have a clutch pilot bearing noise. You can have uh, a release bearing noise, but input shaft bearing noise and counter shaft bearing noise, those are additional noises, and most people do not understand those. So one of my videos on YouTube about throw out release bearing noise was like everybody and their brother had something to say, but then people are totally oblivious to what noises can occur in the transmission. And I did another one on that, and like nobody's making any comments. If you want to know clutch noises, it's pretty simple. Clutch pedal down, it makes the noise, pilot bearing. Clutch pedal up, and you vary it, and the noise changes as you vary pedal pressure, release bearing. That's it. Like that's that to people who are not professional technicians, it's very complicated. But if you heard what I said, I just summed it up. That's it. There's not much to know. Getting into this transmission gets a little more complicated. Now, I'm even going to hurt you a little bit. If you were to have a noise in first, noise in second, noise goes away in third, noise comes back in fourth, and noise continues in fifth, I can already have that diagnosed. Anybody have any idea? I mean, I guess probably no. The noise goes away in third only. All right, this is going to trip you out. All right, but it's going to take you probably the next hour to actually understand this. That's normal. First gear, power flow comes in. This bearing is working its butt. This bearing on the countershaft's working its butt. First gear, this gear is pressed onto the shaft. It's one with the shaft. It doesn't turn. When we go to first right here, first gear gets locked to the output shaft and it sends the power through. What's interesting is that's only first gear. So now first gear is grabbed onto the output shaft. So first gear is no longer rotating on the output shaft, right? However, second gear is driven by the countershaft second gear. So second gear is whipping along, but the output shaft is turning a different speed. So therefore, second gear is running on its own split bearing. Third gear, the same thing. Third gear is running on its own split bearing, right? So you'll see first, second, third, fourth, even fifth, they're all turning. They're all turning, but they're rotating on their own individual split bearings. Remember these? They're riding on these types of bearings. Only when you connect that gear to the shaft does this bearing stop working, because now the shaft and the bearing are moving together. So that bearing's chilling, right? So in first gear, we hear the noise. In second gear, we hear the noise. In third gear, the noise goes away. Let's discuss what happened in third. That third gear split bearing was shot, was no good. That third gear split bearing in Gen Z speak was cooked. And the thing was, that's a problem in first. It's a problem in second. But in third, that cooked bearing doesn't matter because the gear gets locked to the output shaft. So that bearing is just sitting there. There's nothing turning anymore. They move together. Makes sense? So if you had one speed, first, second, third, or even fifth, that was quiet, it's that particular split bearing on the gear. That'd be the speed gear bearing. Fourth tends to be a little bit different because fourth is not rotating on a split bearing. A lot of times fourth is kind of unique. There might be sometimes they'll put like a needle bearing here or something, because remember the input shaft gets coupled to the output shaft. So that one's just a little bit different, right? But there's a whole bunch of bearing noises that you could diagnose just doing different things, changing the gear, changing your vehicle speed, pushing your clutch pedal down, selecting fourth, these types of things. Cool. So if the noise goes away in fourth, it's more like a counter shaft. But if the noise goes away in first, it'd be a first gear split bearing. If the noise goes away in second, it'd be a second gear split bearing. If the noise goes away in third, it'd be a third gear split bearing. If the noise goes away in fifth, it'd be a fifth gear split bearing. Cool. Yeah, a lot of bearings. All right, here you go. This is the R150. So this is an actual, this isn't a diagram. This is the real thing. So here's your input shaft. Doesn't it look like this input shaft goes all the way through? That's why I like this picture, because you can see it doesn't. It stops right there. So right at this bearing, it stops. And then actually right behind fourth, this is the bearing, and then there's fourth. It's kind of weird. It stops right here, but it's sort of hollowed out. So this output shaft is sort of going inside of fourth, but it's not really touching fourth. All right. And then this fourth gear drives the counter shaft, which drives all these gears. Remember, these are the ones that are permanently attached, right? Permanent, permanent, permanent. This one looks like this one could be attached, but a lot of times there's a additional third, a 3-gear arrangement type third gear that'll come in to actually make reverse. So we'll be a little light on that. Fifth, however, is not actually. Fifth is on its own split needle bearing, and fifth has its own sleeve, synchronizer sleeve. So fifth gear would be the only one that's actually the speed gear on the counter shaft. So in fifth, it's a little backwards. Fifth, this is the speed gear that we select, and then fifth turns this fixed fifth gear that turns the output shaft, right? So it's kind of weird, but actually that's pretty typical. And then they might put on a 6-speed fifth and sixth down here on the counter shaft. But if you were to look at this, remember power flow would come in because the clutch is splined to the input shaft. That's your input shaft bearing, right? This fourth gear turns your counter shaft. Your counter shaft's got its own bearing here. It's going to have multiple. And this one's turning its own speed. So all these gears are matched. This is fourth gear speed gear, and this is fourth gear counter shaft gear. Third gear speed gear and third gear counter shaft gear. Second, second, first, first. Now, if you were to have damage on the teeth of the third gear speed gear, and obviously the third gear speed gear has been, how should we say, nesting, if you will, nesting with the third gear countershaft gear. If the third gear speed gear has a broken tooth, what can you also say about the countershaft third gear? Don't make me make this a health class. You know, if this one has some sort of, let me think, debris transmitted disorder, and these gears are rubbing up against these gears, you know this is going to have some sort of debris transmitted disorder, correct? If you got a piece of metal in here and it broke a tooth off, that broken tooth is going to damage this broken tooth. So first lesson here, if two gears touch each other and one gear's damaged, the other gear's damaged, you change them both. You change them as a set. They're partners. There's a term, it's maybe a little offensive, but it's also accurate. Those gears are married. That's what they would call it. Sometimes, like when they make a ring gear and a pinion, they actually run them in a lapping compound and they literally wear them into each other. So they're kind of like one. They're married together. That's an engineering term, okay? So if these gears have to be changed as a set, that's true for these two. That's true for these two. That's true for first. Oh, here's reverse. Reverse swings in over. Reverse is a spur gear on this one. Reverse swings over to the reverse idler gear, or actually more accurately, the idler gear will move over. Okay, so if any of these gears have a damaged tooth, you always have to go with the partner gear too. Same with fifth, same with all these. Here's your output shaft bearing. Anybody know what this swirly looking weird thing is? They don't use them like that anymore. That's old school. That is a speedometer drive gear. So you'd have a little speedometer drive and it would actually spin on that. The faster this spun, the faster it would spin your speedometer cable. And your faster your speedometer cable spun, it would make your needle go up to indicate your speed. It's old school. Then they kind of got rid of that. And then they went into, remember we talked about it in automatics. Then they went into more like a speed sensor. And the first speed sensors were actually driven off of this. Then they started putting reluctor wheels on. And then the reluctor wheels just looking at the tooth, no tooth, etc. Cool. And so there's your overview. Now let's take a look if we were to work on this a bit. Okay, so look what we just did back there. See that change? Fifth gear is off. That's fifth gear back there. Cool. We're moving fifth. Fifth is on, fifth is off. Fifth is on, fifth is off. You can see that. I want to point something out. When fifth is on, you can't see much. When fifth is off, you'll actually notice fifth down here, that's on its split bearing, and then fifth's counter drive, fifth fixed gear is splined in right here. See how there's splines right there? That's how fifth splines in. So it's kind of interesting. And then what do we got here? We're pulling off the reverse idler gear right there. Oops, I went a little too far. We've pulled off the reverse idler gear. Actually, is that the reverse idler? Yeah, that's mainly what we've done. Reverse idler. Okay, and then boom, what do we pull off right there? Who knows what that is? Input shaft just came off. If you notice, with the input shaft off, There's nothing to drive the counter shaft anymore. So now that's how you can kind of see. Your output shaft just has this machined housing, this machined journal, if you will. You could call it a journal. And that machine journal is accepted right here by the input shaft that has a needle bearing right there. Kind of makes sense. In fact, if that needle bearing was really messed up, it would be loud in first, second, third, and then in fourth, when our input shaft is coupled directly to our output shaft, that messed up needle bearing right there would be quiet. So you know. These are all questions I've heard. Roberto, did you just raise your hand?
Yeah, I was gonna ask uh why they take it off, but it was to show the bearing, right?
And during disassembly, this is exactly how we're going to take this apart. And so we took it off simply because we're disassembling this one. So let's just say, for example, you need to change, I don't know, whatever. Let's say this is third. If you need to change third, this is what you need to do. You need to disassemble the transmission like this. So we're really just walking through the disassembly, but at the same time, I can explain a little bit about the pieces and how they work as we're disassembling. Cool. So that's why we pulled the input shaft, which also, by the way, has that fourth gear. So fourth gear is kind of weird. Fourth gear doesn't necessarily rotate on its own bearing. Remember, that's what I was saying. First, second, and third are good examples of those split bearings being bad. But fourth gear is attached to the input shaft. It's just kind of like not attached to the output shaft. Cool. So fourth gear turns the counter shaft. Counter shaft spins at whatever speed it spins, which spins all of these gears. Third, second, first, it's back here. Cool. And then we pulled the input shaft. And then look, now we've pulled, well, what have we pulled there? We pulled, this is called a sleeve. We're going to come back to the sleeve, but now when we talk about the sleeve, you can picture it. The sleeve would be moved by a fork. So the fork slides the sleeve, but also beneath the sleeve, there's another thing called a hub. And the hub, you can be when you can see these splines, you know the hub is off because the hub splines to the output shaft. Okay, so that we pulled the sleeve and the hub. Now you can see the synchronizer ring in brass. We're going to come back to those. We're going to talk about that for probably like 15 minutes. Okay, and then right here, we just pulled second. Or is that third? Oh, we're still on third. So we just pulled third off, third off, third off. And look, like I said, third gear was riding on that needle bearing, that split needle bearing. So what'll trip you out a little bit is if you look at this thing in motion, or even if you take one apart and you turn it, it seems like all these gears are engaged at all times. But in reality, remember, input shaft turns fourth, fourth turns the counter shaft. The counter shaft gears turn all their corresponding partner gears. But those gears, like that one we just pulled off in third, third was just rotating on this needle bearing. It had no connection to the output shaft. So therefore, third's constantly engaged, but it's not actually attached to the output shaft. Make sense? And that's why that third gear would be noisy if this bearing was bad until we put it in third, and then it would be quiet. Because now third would be attached through the sleeve to the hub, right? So it's that part is very hard to see from this picture, but we're going to explain it in cartoons. Now we just pulled that third gear needle bearing. Here you go. And now it looks like we've yanked first off of there. First gear's got a double roller, a double needle bearing. Why do you think? What's unique about first? Remember, bearings, they bear forces. They bear the load. So first gear, make a lot of torque.
That bearing is bigger.
Yeah, exactly. First gear makes more torque, so it needs more bearing. Exactly. See that? We pulled the double needle bearings right there. Cool. Very good. And then I was looking at that. I think that is maybe that's second. I don't remember second looking. I think that's actually the reverse I look. I think that's part of the reverse gear. That's what that is. We're pulling part of reverse right there. because that was where the reverse idler gear was if we were to back way up. Way up. Yeah, there you go. See, that's the one we're going to bring into mesh. When we shift reverse, we're going to move this counter shaft reverse gear is not touching this main shaft reverse gear. When we swing this in, we're going to actually put them into mesh. That's right. Okay, and then as we go a little further, got some reverse parts off. The only thing remaining right there is second. So there's second. Now you'll notice second has its own synchronizer ring. Come back to that. It's got its own dog teeth. We'll come back to that. And it's got its own actual second gear speed gear. So these are the teeth that if they say the second gear speed gear teeth, those are the teeth. If they say the second gear dog teeth, it's these little teeth over here. So we're going to come back to those too. Cool. And then remember, second gear counter shaft gear is going to spline with those second gear speed gear. Makes sense. So this one's actually the most simple that it can get. If we were to be turning the input shaft, turning that fourth gear, turning the counter shaft, and now we split all these off, you can see the counter shaft is going to turn at its speed. And then this is going to be turning at its speed, but that would only be for third. This one's actually for second. So whatever this gear ratio to this gear ratio is, that's really how we're going to get our second gear. Kind of makes sense. So second gear this becomes the drive and this gets driven. Okay, so it'd be driven divided by drive. Cool. And then from here, we would actually spline. So if you wanted to select second, this is the part that gets a little bit weird. This is splined right here. There would be a hub right there, and we could actually connect the hub, click using the sleeve right to these dog teeth. So it's a pretty interesting way that we can grab gears. What I would like to do, I have a whole nother discussion for you guys, but normally I would show you everything I just showed you in motion in an animation. Neutral, first, second, third, fourth. And that animation is really good, but I can't play that while we're doing this. So if right now you're like kind of stuck, just remember you can pause this and you can go watch a couple of animations to kind of see how they shift and how they move. And then we're going to get a little bit more technical. So we pulled that second, we pulled that bearing. There you go. Now let's discuss a synchronizer assembly. So in the video, in the discussion playlist, there's an old school transmission called like a sliding gear transmission. You have one gear turning this way, you have one gear sitting here, and if you wanted to shift, you'd have to bring those gears into mesh. Now, if one gear is turning like this and one gear stopped, it's gonna be very difficult to get those gears to mesh. So the problem was with those sliding gear transmissions, shifting was kind of a beast. Like if you were to go to shift, you might even need a double clutch, which would mean you'd be let's say that you're in first and you wanted second, you'd be in first, you'd push the clutch in, move it to neutral, push the clutch again, and then shift into second very gently. You could probably get it. Clutching twice and giving it extra time will probably help synchronize the speeds. All right. So that was old school. Tractors actually still do that. So like in a typical tractor, you don't like shift on the fly per se. If you think you want first because you're gonna, drag some rippers through the earth and try to catch some rocks or whatever and turn the dirt over, you'd put it in first and you do that. And then if you wanted to drive to another field, you'd stop, put it in fourth, and then let the clutch back out and you could go fast. You don't go burn, 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 burn. You'd have to stop. That's a sliding gear transmission. When they got into making the vehicle a little more drivable, being able to not having to be such an expert to be able to shift the vehicle, they went to constant mesh transmissions. And so this is all about constant mesh. First gear, counter shaft, and speed gear in constant mesh. Second gear's in constant mesh. Third gear's in constant mesh. Fourth gear's in constant. They're constantly meshed. But that's kind of weird. If they were constantly meshed, can it be in first, second, third, fourth, and fifth at the same time? Isn't that kind of weird? So they came up with this design. We got some speed gears here. Let's say this one is first and this one is second. Those are constantly meshed with their counter shaft gears, but neither of them are actually connected to the output shaft. The output shaft ends up being right here. This gray part is the output shaft, but do you see the speed gear is not connected to it? What we do is we slide the hub on there. We call it the clutch hub. These are all the synchronizer components, by the way. So the clutch hub splines to the output shaft. Then what we do from there is we'll use this blue thing, the sleeve, and the sleeve is basically splined to the hub, but the sleeve can be slid over and grab, let's say in this case, first gear. If the sleeve grabs first, but the sleeve is also splined to the hub, and the hub is splined to the output shaft, now you see how first gear would be locked to the output shaft. The sleeve grabs it and locks it. That's the purpose of the sleeve. How do we move the sleeve? Well, when we move the shifter, if you can see, we'll come down here. When you move this shifter, let's say to first, you're actually pulling this rail rearward. And this rail has a fork on it, and the fork literally engages the sleeve. So you throw the shifter forward, it moves the sleeve rearward, click, and this sleeve will come over and grab this dog teeth, and it'll hold the dog tooth right there, which means it's grabbing the speed gear, but it's also splined to the hub. Okay, that's how first gear is selected. Boom. Now there's a little bit more that happens though. The hub also is going to, because it has this shape, when you move the hub to the right, the sleeve to the right, there's going to be these little red keys, and these little red keys are going to shove on this synchronizer ring because this is your problem, right? We have this gear, this first gear speed gear is turning its own speed. Maybe it's turning kind of fast because it's big. And if you're downshifting from second to first, second gear, is like got the output shaft turning at second gear speed, and then maybe first gear is going slow, whatever it is, it doesn't matter. The first gear speed is not perfect. The first gear speed is not going to be the same as the output shaft speed. So when you go to shift it, you're risking gear clash. Like it's going to be like, you can't grab that gear. So what we do, this little red key is going to shove on the synchronizer ring, which is brass. And that brass has a cone clutch assembly. So the brass is going to kind of grab onto that speed gear. It's going to start trying to grab it, but it's going to do that so it can either slow it down or speed it up. It's going to synchronize it. So it's going to get that speed gear turning the speed it needs to turn. And then the sleeve can come over and click, grab the actual dog tooth right there in orange. I'll explain it the very best I can, but in an animation, you can see quite well. The animations just can't play those. Okay, so if we were to take that, and we're going to go back and forward a couple times. So if this was first gear, you can see this first gear are the actual, this is how we get our gear ratio. This is the speed gear teeth. And then right here, see these little pointy things? Those are the dog teeth. And then right here, there's a nice cone clean surface. And that really clean cone-shaped surface is what will accept this synchronizer ring right here. When this synchronizer ring is shoved onto that cone clutch surface, it's going to make that speed gear turn the speed that it should. It's going to synchronize it. Cool. Remember what the keys do? The keys kind of shove the synchronizer ring. They also have a little spring on them trying to expand them. And then this is where it gets a little tricky. The hub in green sits in the center, and the sleeve can slide either way it wants. The sleeve can slide over the hub, press the synchronizer ring, and then grab the speed gear, at which point first gear is locked to the hub. through the sleeve. That's first selected. Then if you wanted to select second, you'd actually move the hub to the left. It would let go of these dog teeth, push on the synchronizer ring, synchronize the speeds, and then ultimately grab these dog teeth, which they'll call the splines. And that would therefore lock second to this hub, which would mean that the shaft will now turn at the second gear's ratio and speed. Cool. So this basically is your 1-2 speed gear, but it's the whole synchronizer assembly. Here's why I say that. If you talk with any ding dong knucklehead and you're like, oh, I got a transmission concern, whether you say I have like a gear pop out, a grinding during upshift, a noise, even a bearing noise, if you say, what do you think is wrong? You know what they're going to say, right? It's got bad synchros. It's the synchro. Bad synchro. Point to me on the screen which one is the synchro. Anybody, please? Where is the quote unquote synchro? Synchro comes from this word. Synchro, and then lazy drop the nizer. Synchronizer components. I count 1, 2, 3, 4, 5 will count all the keys. And that's just for one, that was just for second. So which of the 5 parts? When they say the bad synchro, which 5 parts? If it's got bad synchros, you need to change the speed gear, the synchronizer ring, the hub, the sleeve, the hub, the keys. You could even go with the spring. So if you have bad synchros, you need to change all those parts, but for all the gears, so you basically just change the whole transmission. If it's a bad synchro, you need to be able to define to me what that means. Now, typically, okay, I understand it probably comes from someone who does know, and they're probably like, oh yeah, if you go to shift, let's say 2, 3, and third gear does a little clash, like a little, more than likely, let's make this third now back here. More than likely, the issue is you're moving this sleeve. This sleeve pushes those keys push the synchronizer ring. The synchronizer ring tries to synchronize the speed, and it doesn't. And it clashes. More than likely, your issue right here is the synchronizer ring. But if I ever ask you, I want you to define exactly what you're talking about. Don't say the synchro, because the synchro is all these parts. If you say the synchronizer ring, then I got you. But if you tell me you think it's a synchronizer ring, that's the problem. But what the issue is it pops out of gear. The synchronizer ring doesn't even do that. The synchronizer ring is to synchronize the speed so that the sleeve can grab the dog teeth and therefore select that gear. So here you are, you're mobbing, as they say. When you go to shift, right? Let's say you're in between shifts right here and you're in neutral. So here you go. This is really what you're doing. See how we started to move that shifter back? That shifter's moving back a bit. Starting to move back, but when you really move it back more, I want you to look at this. I want you to look at a couple things. First, let's start down here. It's moving this fork from this perspective forward. It's moving it forward. Ready? You're moving it forward, forward, forward. Went too far. Neutral, fully engaged. Neutral, partially engaged. This is when the synchronizer is being pressed up against the cone clutch. This is when it's equalizing the speed. It's synchronizing, if you will. And then once it's synchronized, click, the sleeve actually grabs the dog teeth. Then the gear is selected. So this was actually a 4th gear shift, right? Neutral, starting to move into 4th, synchronizing with the synchronizer ring. 4th is fully engaged. Cool. That was all your focus should have been down here, right down there. Okay, but what it looks like zoomed in and cutaway is this. Ready? We're going to back it up. This is in the neutral position because this sleeve is centered. You see, actually, this is fully centered. as soon as we start to really move this sleeve, and remember what's moving the sleeve is this rail, which as you can see is connected to the shifter. So when you're pulling back for fourth, which is what we were doing, right? Yeah. When you're pulling back for fourth, you're shoving this shift rail forward. The shift rail has a shift fork attached. The shift fork is shoving the sleeve forward, okay? Now our focus is up here. Right now, the shift fork is pushing on the sleeve. The sleeve is starting to kind of move this key. The key is just beginning to touch the brass synchronizer ring, right? Cool. But as of right now, this speed gear is free to spin on its own needle bearing. So this speed gear is not connected to the input shaft through the hub yet. Now, as you can see, as we continue the shift, the synchronizer ring is grabbing the cone clutch. It's synchronizing the gear, but it's not there yet. And then, oh, now it's all the way there, right? So it was a progressive movement. Push, 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 grab. Okay. So you guys could see that sleeve ultimately through the key pushes on the synchronizer ring, synchronizes the speed, and then ultimately the sleeve ends up way over here, grabbing onto those dog teeth. Make sense? You could see that? Dog teeth. When it grabs the dog teeth, that's when that speed gear is locked to the hub, which is splined to the sleeve, to the output shaft. Okay, that's how it's selected. Cool. Now there's a couple little details. One, right here, you want to notice when we're pushing on it, you can see that speed gear is in orange. The sleeve has teeth on it, and they put a little like a chamfered edge on here. And that's basically so that when you bring this hub into position, it might actually bump the synchronizer ring, and it actually might like bump the dog teeth like this. Like you go to shift and it's like this. You're like bound up, gear bind, boom. You can't shift. If you ever have a car and you're always like, if you ever try to shift it and you go into that gear and it feels like you're forcing it, this is why. You might just have had the sleeve tooth come right into contact with the synchronizer, right into contact with the speed gear dog teeth. But they put a little chamfer on there so it'll basically knock it down to where it needs to go. See right there? That can take a bit of effort. Right? Initially they're gonna hit and they're gonna be like, uh-oh, but then they have an angle on them, so it's gonna be like, yeah, go like this. There you go. There you go. But you can feel that sometimes. That's normal. What somebody was saying yesterday, once in a while they'll go to shift and it'll kind of like bind up, and then you might have to sort of like switch to another gear and then it'll go in better. That's because if you switch to, let's say this was fourth and you switch to third real quick and then to fourth, third a lot of times might spin this hub a little bit, and then the hub might line up perfectly with fourth. It's just, the manual is a gearbox. There's a lot of gears and there's a lot of parts. So when you want to go into fourth, there's quite a bit of things that have to go into alignment. And sometimes they might not line up just perfectly. Sometimes also what helps is if the vehicle's rolling a bit, because if the vehicle's rolling a bit, that would mean your output shaft is rolling a bit, which is turning your hub, which is rolling a bit, which could actually help turn the sleeve a little bit. And if something's dead stopped, it can go like this. But if something's moving a bit, it could be like one's moving, right? So here you go, slips right in there. So that's why sometimes on a roll, it's actually easier to get it into gear, or sometimes even into reverse, first to reverse. So this is just the mechanism, just the way it is. Cool. So that one mostly showed it. I thought that one was really good. It's like a fake animation. Then to go into a little more detail here, like remember I was picking on I'm picking on the unnamed person who talks about synchros, bad synchros. Okay, like just stop. When we get into the actual gears, I want you to notice something. Blue is the sleeve. The sleeve has teeth. Orange is the speed gear. The orange has teeth. They have an interesting little relationship. They have what's called a back taper. So what that basically means is when we slide the hub onto the speed gear. Right here, you'll notice the like on the blue on the sleeve, it's a little fatter and then it gets a little skinnier. And then same with the speed gear, it's a little fatter, it gets a little skinnier. That's what they call the back taper. It's back cut. That pretty much means when you go to engage it, it's going to be actually really tight. You got the fat part to the fat part. That's going to be kind of hard. But then once you get past that, you get the thinner part to the thinner part. That's on purpose. When you're in gear, now do you think it's going to be easy for, let's say, this sleeve to slide out to the left? Because there's a back cut right there. It's going to be hard to pull this out. We do that on purpose. That's why it doesn't pop out of gear. Make sense? So we back cut those specifically so it doesn't pop out of gear. We do the fat part to the fat part, and then when we engage it, we actually push the fat part past the fat part. Then that means to disengage it, we need to pull the fat part back past the fat part. But it shouldn't do that on its own. If you let go of the shifter, it should stay in gear. If you let go of the shifter and it ever pops out, that's a legitimate transmission concern. That's called gear pop out. That is generally going to have to do with the back cut taper on either the sleeve or on the speed gear. That has nothing at all to do with the synchronizer ring in any way. The synchronizer ring's job is to get them synchronized. So that'd be grinding on engagement. The back cut dog teeth is going to be a pop out. They're totally two separate, completely different issues. Here's some worn out. Here's a good, nice fat part. And then here, these ones are kind of like worn out. That sleeve, especially this one looks something like one of the worst ones. That sleeve could be engaged on the speed gear, but you can also see how it could pull itself off too, right? This sleeve is worn. This sleeve is good. So if you're doing a transmission, it'd be nice to know if it's got pop out, but also if you don't know, you got to look at this very carefully. You got to know what to look for. You notice how this one's nice and clean, and this one's actually been worn too much in this angle. I'll give you a good story about pop out. Anybody have a car that does gear pop out? Didn't think so. I got one. So my dad's original truck was an 86 Nissan, and Nissan and Toyota, they were kind of similar back in the day. Now Nissan's kind of gone a different direction. But back in the day, the Nissan truck and the Toyota truck, they're both pretty cool. In 86. Four-wheel drive. So he probably would have bought a Chevy, but he didn't have the money, so he bought a Nissan. It was a great truck. It is not a good truck to put a snowplow on. Snowplows weigh a lot. They hang way off the front. They're hard on the suspension. You block a lot of the airflow. Like, honestly, if he was going to plow snow, he should have put it on a Chevy, right? But he had a body shop, and so he had a little tiny driveway to plow. And plus, where we were at, we got a lot of snow and stuff. So he got the Nissan. He put a ton of miles on it. The thing was already pretty beat. It had like 350,000 miles. He put the plow on there, and then he would mostly use it as a plow truck for the little tiny parking lot, like the driveway. We'll just call it the driveway. When you're plowing snow, this is what you do. Like if it were me, and if I went up to the garage door, I'd lift the plow, I'd put it in first, I'd drive up to the garage door as close as I could, I'd drop the plow, boom, put it in reverse, back drag the snow out at least like 25, 30 feet, probably 30. And then I'd put the truck in reverse, back up, put the truck in first, pull forward, put the truck in reverse, back all the way up to the driveway, drop the plow blade, put it in first, push the snow out. Probably have to back up, put it in forward, reverse, first, reverse, first, reverse, first, reverse, first, reverse, first. You get my point? When you're doing something like that, you're in first and you're in reverse all the time. So after all that shifting, right, we had to move this sleeve on and off those dog teeth hundreds of thousands of times. By the time you're driving it a lot of miles and then you're using it as a plow truck, it's just first reverse. So if you had to guess, what gear you think it was popping out of? Third, fifth? Pop out of first. It had been put into first and pulled out of first so many times. Pretty soon it was probably going to pop out of reverse, but all the wear was from engaging and disengaging. You can see it's on this side. That's when you're putting it in first and it's, you know, trying to go. That'd be like the drive side. So what would happen? You'd put the truck in first, and if you tried to drive with two hands, you even under load, you'd try to drive and it'd be like bam, and it would pop out zing in neutral, and you'd have to clutch and get it back into first. And then by that time, you lost your momentum, and like it's kind of hard to get it moving, especially when you're pushing a snowbank. So basically, the way you drove it is you'd hold it in first the whole time. You just hold it in first and drive with one hand. That was really tough because the plow control was like on the like mounted to the dash. So you like have to put it in first and kind of drive and use like your left hand to try to move the plow up and down and left to right. It was a disaster. But the real ultimate problem with the transmission was this. It would have had a worn sleeve, but the other thing you got to remember is it can wear the dog teeth on the speed gear as well. So now I know a little bit more. If I wanted to fix that, I would have pulled the transmission out, disassembled it, got to first gear, replaced the first gear speed gear in the first second sleeve. Because remember, the sleeve always does two gears in the gate, right? So first and second are like this, right? First, second, it'd be the sleeve for first and second, but I'd probably just replace the first gear speed gear. Now, if I got in and second gear looked, you know, like this on the speed gear, well, then I might do more. Right. So that's your perfect example of a pop out. Make sense? Now let's go with, does anybody have a car that grinds into a certain gear when you upshift? Anybody? Nobody here? I'd be a bit surprised. Okay, we're gonna make a, let me take a look at my list so I can make this fun. You guys can report this to Colin. We're gonna fake pick on Colin only because he's always a good sport and he got his transmission pretty nice and hooked up. Let's just say Colin is there driving a Subaru, living his Subi life, and first is good, second is good. When he goes into third, a lot of times there's just a little something, like a little, just a little. And when you really try to shift fast, it'll grind third. But if you shift really slow, it probably won't grind third. That would be a notorious, perfect example of a bad synchronizer ring. Now, this one happens to be a two cone. But if we were to back up, the more basic synchronizer ring would look like this. It's just one piece of brass and it's got sort of like some grooves cut into there and they're actually pretty sharp, but it's brass. So if we shove the brass onto the cone clutch, it's not hurting the steel, it's brass. So every time you shift it, and this has to equalize and synchronize the gear speeds, there might be a little tiny bit of wear on that synchronizer, a little wear on the synchronizer ring, a little wear on the blocker ring. By the way, they'll call it a blocker ring sometimes in ASE. That's more of a domestic term. Synchronizer ring, blocker ring, same part. Cool. A little wear, a little wear, a little wear. So what Toyota did that was kind of smart was they started making the speed gear like this, and then you'd had two parts to the synchronizer. There was a brass part, and that would engage a separate cone clutch, and the cone clutch wasn't necessarily part of the speed gear, but its little legs would engage it, so it would function like it was part of the speed gear. But technically, if you wanted to fix this, you could actually do, this would be your synchronizer assembly. You do the inner ring, the cone clutch, and the outer ring. So let's just say the brass continue to wear a bit, a little bit, a little bit, a little bit. Third gear wouldn't synchronize that well, right? Third gear would be turning its own speed. You were moving second gear to the output shaft. And then when you go to do third gear is like lagging, you know, maybe third gear's not spinning as fast or whatever. And then you go to catch third, there's a speed differential. The synchronizer should synchronize the two speeds and then make an engagement of the sleeve very clean. Click, cool, click. But instead, it's like, no, I'm all worn out. Yeah, you can shove me towards third. And it's like third gear, whatever. I don't even care. If they're going a different speed, that sleeve is going to kind of grind onto those dog teeth and you're going to feel something. Cool. So if you were to say, yeah, on third gear engagement, it grinds if I try to shift fast. But if I shift really slow, it doesn't really grind. It'd be like, yeah, your synchronizer rings are starting to get there. They're worn. Cool. Okay, let's give it the part of the reason I was thinking Colin was I want to give it another option. If you have what Colin had on his Subaru, which was some worn shifter linkage, I want you to think about something. Worn shift linkage, when you go to shift it, that shifter linkage is kind of sloppy, right? So if he were to grab, let's say third, and then be cruising in third, and it pops out, you'd kind of be thinking back to these dog teeth, his back cut, right? But what if I were to say it tends to pop out of all gears randomly? It'd be like, what? What do you mean it pop? Then they're all worn? Well, maybe. But what about this? When you go to shift it, it tries to hold it in gear. And there's a couple other things that do as well. But if your shifter linkage is so loose, that shifter is able to swing, it can actually fall backwards and tug on the actual shifter linkage and yank it out of gear. So Colin had a pretty cool one. His shifter linkage was like literally like this. So if you're driving and the shift, there's so much linkage, the shifter can actually build up enough momentum to pull it out of gear. It could make a pop out in all gears, potentially. So generally, grinding is going to be related to the synchronizer ring. Pop out is generally going to be related to the dog teeth, the back cut. But if it's popping out on all gears, it might be more related to the shift linkage being really loose. Well, remember how I said it was grinding into third? What if I had a vehicle such as this Jeep, if you'll remember from last week? When I go to put it in reverse, it grinds. But I were to take it out and drive it, it kind of grinds going into first, it kind of grinds going into second, it kind of grinds going into third, grinds going into fourth, grinds going into fifth. And there's some other symptoms. What are your thoughts about it grinding in every gear? It could be worn synchronizer rings in every gear, right? When we go to do a shift, what's one of the important things that we need to do first before we start the shift?
Press the clutch.
Yeah, so if you're pressing the clutch pedal, but there's air in the system or your adjustment is too short on the push rod, your clutch will not completely disengage. You'll continue to transmit torque. That's going to make a gear clash too. That will grind, but it would grind in all gears, right? So consider the typical grinding and the typical pop out, but also consider overall, if it's happening in all gears, it could be an external factor. Make sense? Pretty cool. And then Toyota came up with the even cooler one, the 3-cone synchronizer. So they've had a couple different variations. Pretty neat. Overall, whichever type it is, it's not a real big deal. We're going to be looking very carefully at these dog teeth, right? We're looking at the back cut on the dog teeth. This one looks like it has a little wear. We're going to be looking at the synchronizer ring. Sometimes what I'll do is I'll actually run my hand across these lines, and if they feel sharp, that's a pretty good indication. Another way to do it would be to put the synchronizer ring onto the speed gear and see if it grips it, and it should grip it. It should grip it really well. If you can push hard like this and it can still spin, that'd be no good. Make sense? And then even better yet, if you think about it, if this synchronizer ring, if these little lines and these little grooves wear, the synchronizer ring is losing material, right? That brass, by the way, will end up in the oil. So if you ever drain manual transmission and there's brass, that would be from a synchronizer ring, generally. Okay, that'd be a problem. But as it wears, it'll slide further and further onto the gear, and you'd get a lower and lower feeler gauge reading. So we're checking the clearance between the synchronizer ring and the speed gear dog teeth. And that will tell you the amount of wear that's on the synchronizer ring as well. We don't ever really factor speed gear wear because the speed gear is steel. So against the brass, it doesn't wear. The brass always takes the wear. So these are a couple ways to evaluate whether the synchronizer rings are good or bad. But wait, there's more. Here we get into how it shifts. So here we go. Let's say that we talked about the gate, the shift gate a bit. But we're going to talk about it some more. If you go to pull this in first, you know that's going to move the shifter over here, right? And forward. So that would mean the bottom of the shifter is going to shove its little ball over and grab this rail. And then when you shove this forward, it's going to pull it back. So this rail right here would get pulled rearward. That'd be first, right? And then when you pull it to second, it goes back, which shoves it forward. So what I'm saying right here, this is the 1-2 shift rail. The 1-2 shift rail is going to move the 1-2 shift fork forward and back. Cool, makes sense? Now, when we do that, I want you to note it has what's called a detent. And what a detent is, it's this little, it's kind of like this little ditch. It's almost like a little ditch. It's a detent. This ball wants to be pushed down into the detent because the spring is pushing the ball. So right now it's in neutral. It's in the middle one. When you pull it into first, this is going to slide back, which means this ball is going to have to be pressed up against the spring. The shift rail is going to move back, and then the ball is going to pop down into first. So this is a detent. That's what, when you get when you have a car, it's pretty new, the shift feels like tight. It's like, this is nice. It's like there's neutral. First almost feels like it clicks in. It gives you a confidence of like, I know it's in first. They do that using this spring, ball, and detent, the notch. Cool. Then neutral, it'll kind of stay in neutral. Second, boom. It's a crisp, tight engagement when this is working well. Kind of makes sense. And then if you center the shifter and then you go this way, that'd be third, fourth, right? So third would basically, the bottom of this would let go of this fork. But to let go of this fork, you have to center it first. That's coming up next. That's the interlock. You have to center the 1-2, let go of the 1-2 and grab the 3-4, and then you can do third. Third would again force this ball up against the spring and drop into this detent, which will locate third. What's happened mechanically though is when we were in first and second, we were moving this fork. Remember the fork? The fork moves that sleeve. So the sleeve engages the dog teeth. The sleeve also, remember, is what initiates the synchronizer action too, right? So when you're doing that whole synchronizer thing, you're doing that with the shifter, and the shifter is moving these rails, and these rails are moving the fork, and the fork is going to move the sleeve, and the sleeve is going to do that other stuff, and then ultimately lock a speed gear to the output shaft through the hub. Makes sense? So there'd be 3-4 right there. Cool. And then here would be fifth reverse, or, when you jump in the car and they have reverse behind fifth, you know that it's fifth and reverse. But when they put fifth on its own, when they put reverse on its own thing over here above first, that more than likely means reverse is on its own little shift rail. It's got its own little shift fork. So they can put reverse in several different spots. On a 6-speed, this would obviously be 1, 2, 3, 4, 5, 6, and then reverse would for sure have to be on its own rail. So when they talk about like something that's been on the ASE in the past, is you're using this shifter right here, and this shifter is moving these different rails. If you were to go to the first, second rail and have it be very hard to move like this, but then you were to go to 3, 4 and have it be easy, that would be a pretty good indication that this shift rail would be binding. Makes sense? Or if you were to go to 1-2 and it was not to be able to engage first, but it can engage second, it might actually be the 1-2 shift fork is bent. Okay, that could happen too. If you were to, an interesting thing I've seen on there is they say first, second work, third, fourth work, but the fifth and sixth is missing a gate. You're like, what the heck's that mean? That would mean these two would engage, but when you go to fifth, right, you got to go all the way over and right. It'd be almost like you can't get all the way over there. You can't do fifth or sixth. You couldn't get there. That might actually be like a worn bushing right here. If this bushing is worn, it won't move all the way over to grab fifth, sixth, because you're trying to move it, but a lot of your movements, going towards the looseness of the bushing, and it doesn't actually get the bottom of the shift mechanism far enough over to grab that rail. So there's some kind of interesting things that could happen there. Things to consider. Additionally, we could have like a spring or detent problem, and that rail would go forward and back really easy. And that could actually contribute to pop out in that particular gate. So if it was the spring in the ball and it was on this rail, which gear or gears would probably pop out? You guys remember? You got no spring and no ball. That means that rail's very free to slide back and forth. That's like the 1-2 shift rail. So you put it in first and there's not really much holding it in first. It could pop out of first, but also you put it in second, there's not much holding it in second, it pop out of second. So if you have pop out on first and second, I would start to suspect maybe an issue with the detent and the ball and spring, more so than just the back cut dog teeth. Arr. See the point? All right, and then you can see it a little closer. Here's the notch, here's the detent ball and the spring. So right now that's in neutral. When you go into first, it goes back, so this ball will drop into this spot, right? The ball doesn't move, actually, the rail moves. Kind of get me? Kind of get what I'm saying? Cool, so those could contribute to pop out. And also those are what make it feel like crisp, confident, confidence-inspiring engagement, if you will. Now here's something similar, but different. This is the shift interlock. Okay, so the detent mechanism was for feel, and mostly for feel, but also a little bit to make sure it doesn't pop out of gear. The shift interlock mechanism, this is to make sure you don't grab two different gears at the same time. If you had two different gears, if you had first and third both attached to the main shaft, it can't turn at both speeds. Something's going to break. Makes sense? You're done. I even had a coworker, and I specifically recall he was late to work one day and he called, the guy, my mentor worked next to him. This guy worked next to my mentor. And so he's like, oh, yeah, Frank's going to be late today. I'm like, oh, okay, interesting. And I remember specifically, he's like, he came in, he had his 99 Z28 Camaro on the back of the tow truck. So he had a little bit of a racket, I'm going to tell you. A racket meaning like a questionable ethical situation. So he bought his Camaro, but mostly he did it through his wife's name. If that Camaro ever broke, it was written up under his wife's name, but he would bring it in, he would assign himself as the tech, and he would get paid under warranty to fix it. Okay, so you see where I'm going with this. He drove that car. You know the saying, he drove it like he stole it. I would even go further to say he drove that car like it was under warranty and someone else had to pay for fixing it. And he got paid to fix it. So there was some things there. But I remember, I mean, he drove like a wild animal. He'd full on like if he would race somebody, his license plate was UR Slowsome, by the way. That was his thing. And he beat a lot of people, a lot of cars that his car was faster than theirs, but also some people that should have won, but he just drove like a maniac. But back in the day, the 6 speeds were faster than the autos. So if you could shift fast enough, you'd beat the autos. But if you could shift faster than the person in the car next to you, you could also beat them in a manual. It's like he was just kind of a nut. But he would drive it so hard in first. When he would go to first, second, he wouldn't clutch, he wouldn't let off the gas, nothing. He would full on just rip it into second without even letting off. It was pretty wild. Crazy sounds it would make. So anyway, in no shock, next thing you know, he's on the side of the road and his shifter's loose and sloppy and the car won't move. It's totally bound up. All he can do is push the clutch in and come to a roll. As soon as he lets the car go, it just stalls. It will not move. And what he found out was it was actually in two gears at once. He broke the shift interlock mechanism. So it's interesting because he was on like a toll road type of thing. And the toll roads, a lot of times they'll have their own truck driver, so that way they keep the traffic flowing so they can bill you the toll. And the guy shows up, he's like, "Hey, how can I help you today?" And he's like, "Well, my transmission's stuck in two gears at once." And the guy's like, "I can help you with gas, flat tire, jump start." transmission stuck in 2 gears at once, I can't help you. Turn around, got in this truck and left. This is like not a small problem to fix. This is why that should never happen. If you look at this, you see this has this interlock pin. A former student called it a pill. It's got a little pill. It doesn't. It's the shape of a pill. So if this pill interlock pin is shoved into fork number 3, and there's also a little pin right here, and then that pin is pretty tight with this interlock pill. The only one you can move right now is shift fork number 1. You can see. So if you want to move shift fork number 1, you can do that. Cool. That'll give you your 1, 2. But let's say you want third. Okay. Do you want third? No problem. Then what you need to do, you need to center this one first and then try to move to third. And then look, third will push the pill into the 1, 2, and the other pill into the shift fork for 5th and reverse or 5th and 6th. Okay. But at no point should it ever be able to move both. It should never move both. It's not supposed to move both. Moving both would be exactly what happened to Frank. He had 2 shift rails out of the neutral position. This shift lock mechanism should prevent that from ever happening. It should only ever allow 1 rail to move, right? You want this rail, no problem. You want the next rail, you got to center it. You want the next rail, you got to center the middle one. Cool. But he actually broke the interlock pin. He broke the pill, snapped it. Can't imagine why, but he broke it, and it was literally in 2 gears at once. Done. So if a transmission is able to get into 2 gears at once, you can suspect the interlock mechanism. It's very simple. It's literally the pill or the pin. That's it. Okay, so simple. And now sometimes they'll do a couple different things, like if you had a vehicle, and I saw this once too, and some people were kind of racing and horsing around, and he went to do first, second, third. No, I think he went to do, let me think, where was reverse? I think reverse is in the top left. These guys were racing, and I'm pretty sure one of them meant to do a 2. No, I think they meant to do a second to first downshift, and they actually, I don't know, let me rethink this. I think reverse was up in the top corner from 5th. I think that they were racing, and he did 1, 2, he tried to hit 3, missed it, and didn't hit 5th. He blew right past it and got into reverse. I remember them saying, when you were racing and you passed me, I saw your reverse lights come on. So like, a missed shift could be very damaging. Like, we were getting a lot of 86s in a while back, and they would have the rocker arms blown off of them, but it was always on a manual. And we think what was happening on a lot of those was they would miss shift, right? If you're first, second, third, and then you go to hit 4th and you miss and you hit 2nd, you'll over rev the engine. Now, yeah, you have a rev limiter. The rev limiter will do fuel cut, but the fuel cut won't stop the engine from being over revved. If you shift into 2nd at 70 miles an hour, 80 miles an hour, that's gonna over rev it mechanically. Fuel cut won't stop that from happening. So if you do a misshift, you can over rev an engine. Some transmissions, they'll actually do some level of misshift prevention. So they might do like a different restrict pin, and they can have a weight. And if it's spinning too fast, it'll actually not allow your shifter to go in a certain position. Or a modification of this, and that's not real common, but a modification of this is like in my Camaro with the Tremec TR 6060, I think it's called. It has a fuel savings mechanism, like a 4th gear skip shift. And so you'll try to go from first to second, but like if it thinks you'd get better gas mileage by being in 4th, it'll actually punch out a little solenoid. It'll hit your shifter and it'll knock you into 4th when you're trying to go to second. It's kind of weird. You're like first, you're going second. It goes boop, bumps you over, and you hit 4th. And you're like, and then, what the heck is that? Fuel economy and emissions, right? So they can do some things to prevent a misshift, but generally they don't do a whole lot. One thing they will do for reverse sometimes is this. When you go to get reverse, you need, let's say this mechanism, when you go to do reverse, it actually has to contact and push on each other. And so sometimes what they'll do, they'll have like a weight right here. And the faster you go, this thing will spin out of its way. And then when you go to do reverse, it actually won't contact it, or it'll do the other way. This thing will spin in the way. And when you go to shift reverse, this gear, this little arm will hit this arm and it'll block it. So, like, see this one? We go to hit reverse and this one's actually blocked. So basically, this red thing is going up against this spring, and the faster you go, it'll actually spin it up and block it. But if you go slow, this thing will fall down and just kind of be out of the way. But if you go fast, it'll spin up and block it. So they do some interesting little mechanisms to prevent you from actually going into reverse. But do you want to know the only real way to guarantee that someone doesn't miss shift? You eliminate the manual transmission. You then go to an automatic, and when the customer gets the paddle shifters, the sport mode, and they try to shift in the wrong gear, the computer just says no. So they've tried some things because they've had some damage with this. There's no perfect way to get the manual to be dummy proof, if you will, but they will do a few different little things. Cool. And similar, like when you do reverse, sometimes they'll do reverse one way and etc. And then, like, for example, with this one, if you want to go into reverse, you have to center this fork before you can move the reverse shift fork. This is just a continuation of the interlock mechanism, right? So it's even though reverse might be on a different shaft, it won't let reverse move unless you're in the correct position. And it won't let you go into fifth unless you're at a reverse. It's continuation of interlocks. And then this was the thing. Back in the day, reverse was a non-synchronized gear. So if you were slightly rolling and you tried to go into reverse, it would grind really bad. And people were kind of annoyed because, sometimes when you're driving, you might be going 1 or 2 miles an hour and try to catch reverse. So what they did was they put in this pre-bulk mechanism, which all it is they just synchronized reverse. So first, second, third, fourth, fifth, and even sixth was synchronized, but reverse was not. And that was kind of like, well, it grinds sometimes and it's annoying. I don't want to hear that. Cool, we'll synchronize it. So actually, reverse can be synchronized on some. And that's why you can go into reverse if you're rolling just a little bit. Cool, that's what this whole mechanism is. So it's pretty neat. And then that's transmissions. Now you're going to see transaxles are very similar, but there's just a couple little basic differences. Main difference, our input shaft drives our output shaft. We don't really call it the counter shaft, but you could, because it does spin counter, it spins backwards. But you notice there's no like input shaft, counter shaft, output shaft. It's really just two shafts. Cool. And then additionally, your output shaft has a drive pinion on it, and your drive pinion is going to drive the ring gear of the differential directly. So there's no drive shaft. There's the output shaft driving the differential directly right inside the transaxle. Cool. Beyond that, it's kind of similar. Because we have the differential in here, where we may use a different type of fluid, sometimes use the same fluid. On some of the older ones, they had a type of fluid for the like the transmission part of the transaxle and a different fluid for the differential part, but that's going way back in the early 90s. Now it's all just one. It's not a real big deal. It's pretty similar to working on a manual transmission, except it's just got a little differential in there. Not a real big thing. All right, so if we go and look at that differential itself, you guys can see this is going to be your output shaft. We may call the pinion, and that output shaft pinion is going to drive this brown gear, which is the ring gear. Now they'll call it a final drive because that's the final gear reduction. So what's a little bit of a pain is it's harder to understand because if you're in fourth and that's 1-to-1, you get 1 RPM on the input and you would get 1 on the output shaft, but then it goes directly in the differential. So the differential has its own gear reduction of about 3 point something or 4 point something to 1. So it's kind of harder to tell what's 1-to-1 because it's all turning. Right. But other than that, not a real big deal. From the differential, if we spin this ring gear, we're going to turn this blue part. And this blue part is going to ultimately try to turn the axle shafts, but the axle shafts are actually splined into side gears. That's entirely a differential discussion. But I want you just to remember it for now. We got a full-blown differential in here, which we're covering next week, by the way. Back in the day, this differential was driven by hypoid gears, which would mean we need a special type of oil. Now they typically just use like helical cut gears. So it's not even really any different than regular gear oil for a transmission. Cool. All right, so if we look at this transaxle, for example, here's your input shaft. Your input shaft has 3rd, 4th, and 5th speed gears on it. But then your output shaft actually has 1st and 2nd. So when we go to shift, we're not necessarily shifting, the speed gears are not necessarily all on one shaft. When you go to shift, you might be moving gears here, you might be moving gears here. Not a really big deal. But depending on what gear you're in, this would be your input gear and this would be your output gear. So this would be your drive and this would be your driven. So if you wanted to do the calculation for first, you would count the teeth on first, driven, divided by drive. You'll see there's a lot of driven and a little bit of drive. So this might be like a 4. Let's say there was 40 right here and 10 right here. That's how you get a 4-to-1 in first. And then let's say in second, there was 30 here and 10 here. That's how you get 3-to-1. That'd be 4-to-1, 3-to-1, or these types of things. Now, if you look, this one's kind of fun. Back in the day, they had a 4-speed, right? So the 4-speed actually ended right here. What they did was when they started needing really like 5 speeds for fuel economy emissions, they really just started adding like a little extension. So even some of these literally looked like just a pan on the back of them, and they would add 5th gear to the back. So if you guys pull one of these apart and you pop that rear cover off, you'd be like, oh, there's 5th right there. 5th is kind of outside because it was really designed to be a 4-speed, and then they add 5th later. So the 140 was 4-speed, and then the 150 was 5-speed. But then as we got a little bit further, we got into the 6 speeds. You see that like this is a little more traditional. It looks like 5th and 6th were more planned. Whereas back here was like, well, it could be a 4-speed, and then bang, they could add this on and have it be a 5-speed. The 6-speed was designed with 5th and 6th in mind already. Cool. So in the 6-speed, you got reverse, you got 1, 2 are still on the output shaft. Pretty much everything else is on the input shaft. The way it works is going to be very similar. And then here's the E, and we got several options. The way it works is going to be similar, except, and some transmissions do this, but not that many. A lot of transaxles will actually have a little oil pump. So in a typical transmission, the gears are just splashing in the oil and they lubricate themselves. In a transaxle, sometimes the shape of it's a little awkward. Sometimes we got to pump oil to the differential, but we also got to make sure that the gears are being lubed for the transmission side. So we may put a very basic oil pump in here. So there'll be like a simple strainer. It's not really a filter. It's just like a screen. And this pump will be driven sometimes off the differential ring gear. So as long as the differential's turning, this pump will be turning, and it'll just pump some oil to the various locations it should be. You might even occasionally see a little transmission cooler. Cool. So that's one slight difference. And then the reverse is actually the same. The reason I combine these is because some of these help you understand a little bit better. But here's your reverse gears. In this transaxle specifically, they're not constantly meshed, and that's pretty typical. If you wanted to engage reverse, you'd actually need to move this gear up and literally spline it to this gear. And that's gonna, that would make some noise. And that's why you really need to do it when you're stopped, right? So all the gears are constantly meshed using synchronizers, except generally reverse. So reverse actually is a sliding gear. And that's why reverse will tend to grind. So if the customer says, oh, sometimes if I'm rolling and I put it in reverse, it grinds, you can't fix that. There's no way to fix that. It's a non-synchronized sliding gear, and we have to actually engage. See, this is part of reverse, and this one over here is part of reverse, but they don't touch. So if this one's turning clockwise, this one's not turning at all. If you bring this gear in, this will turn clockwise. It'll turn this gear counterclockwise, and it'll turn the output shaft clockwise, which turns the actual differential counterclockwise, and that's why it's in reverse. Cool. So it's kind of, we add a gear in the mix, and that's how we change direction. That's what I'm saying. The input shaft doesn't change direction. The output shaft actually does. Cool. Now, how do we shift it? Well, because the transaxle is no longer like in the tunnel right below where the shifter is, we a lot of times will have to use cables. So push-pull cables would be like basically one of these. If you're going left to right on the shifter like this, one of these cables will control the left to right. And then if you're going forward and back, one of those cables will go forward and back. So if you pull the shifter left and up, one of these cables is going to go push, and one of these cables is going to go push for up. And then if you pull it down, one of these cables is still going to be push, and the other one's going to do pull, and that's going to click second. Then when you center it and you go over to, let's say, fifth, that one that was pushing is now going to pull, and then going up to fifth is going to pull, right? So essentially, these cables are doing the same thing that the shifter would, except it allows us to mount the transaxle next to the engine, and it allows us to have the shifter remotely mounted up here where we can actually control the shifts. Cool. The positives and the negatives. Well, the positive is we can mount it wherever we want. The negative is these cables could require adjustment. If you had a problem with an adjustment on one of the cables, it may make it so that you can't catch any of the forward gears. If it won't push far enough, you won't be able to click first, third, or fifth. If it won't pull rearward enough, you won't be able to click second, fourth, or reverse. Kind of makes sense. Should you have to adjust these? Not really. They're adjusted from the factory. The only reason you'd have to adjust them is if you unadjust them somehow. So there's a procedure, but it's not real common. When you go to pull that transaxle, that's why you're going to be pulling these little safety pins and popping these cables off and then folding them up out of the way, because that is your shifter right there. In a rear wheel drive, the shifter probably comes up through the floor. So you're actually probably going to have to undo the shifter. That's something that we got coming up towards the end. Show you a lot of the different procedures that we do. Cool. So here's what that shifter looks like down on there. It's almost like a little shift drum type of thing. It's a hammer. When you move this way, that's going to be, that's like, let me think. That's like this. Then when you go this way, that's going to be like this. Click, 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 click. Depending on what you do, it's going to grab each one of these gates. So if you look at this gate and you pull it left and forward, that's going to plunge inward and then this direction, and that's going to grab the shift fork because it's going to go in and grab this little yellow gate and throw it forward. Cool. Then when you pull it backward, it's going to go backwards. So just understanding this thing selects the different gears by selecting the different forks. So you can see this, let me look at that for a quick second. You can't see it real well. This is actually where the cable connects, but inside there would be a little arm that would drop down, and it will grab either green, blue, or yellow. And then if you grab green, that's fifth, and in sixth if it had six, but this one only has fifth. If you grab blue, that's going to be 3, 4. If you grab yellow, that's 1, 2. If you want reverse, you actually have to go to a different gate and you have to grab reverse. So this is one of those ones that reverse would be like off on its own somewhere because you got to grab a different shift rail, which will move the fork. Cool. And then if you look right here, see these 3 things? Those are the shift detents. That's what gives you that crisp feel. That's all the same as the transmission. None of that's really any different. They do a better job on some of the shift fork things here though. So there's your detents. The detents, a lot of times you can actually access those from outside. So we have seen a couple times where someone sees a plug like this and they're like, oh, what's in the plug? And they take it out thinking that there's like maybe they add fluid there or something and it pops out the spring and the ball. And next thing you know, the shifter's sloppy. You could actually service the detent externally. You don't have to take it apart. So that's kind of a cool little detail. And then if you look, this is pretty much the same as an interlock. It just looks slightly different. So this is the interlock mechanism. And then again, the reverse will have its own little one-way mechanism to make sure that when we swing that idler gear in, it can't be in fifth at the same time. Not a real big deal. It's again similar to the transmission. You obviously can't be in fifth if this gear is moved, if this shaft is moved, you can't move this shaft, right? It's just an extension of the interlock. So that's how you know you can be in fifth, but not if you're in reverse. You can be in fifth, but not if you're in third, right? Not a big deal. If you wanna shift, you got to center this, and the ball is gonna have to drop in, and then you can move this shaft. Cool. Right now, you're not going to be able to move this shaft because the ball's not there. So you got to let them drop down in, then you can move that shaft. Cool. Same as the interlock. Okay, now the bearings can be a little different. So here's your input shaft. There you have 2 input shaft bearings. Sometimes you have a basic roller bearing. Sometimes you have a bigger input shaft bearing back here. The bearing at the back tends to be bigger on this one, so it's a little different. And then you have your output shaft has a ball bearing. These 2 are really heavy duty back here. Then in the front, you may have a roller bearing. The tough thing is if you wanted to change these roller bearings, sometimes you can undo a bearing plate. Other times you got to totally gut the transaxle. So it can be a small job or a big job. And then in your differential, typically you're actually going to have tapered roller bearings. So the tapered roller bearings require preload. So all this is the same as a transmission, but down here, if you're working on this is differential stuff. We're not going into differentials too much right now. That's next week. Cool. And then if you look at this is essentially kind of the same. It looks very much the same, but I feel like they did a really nice job on this animation, maybe better than transmission. So if you look, here's the sleeve. You go to shift, look, it starts to push on that synchronizer ring, pushes the synchronizer ring down. You guys tell me, what's the purpose of pushing the synchronizer ring towards the speed gear? Why would we do that? What is the purpose of that brass synchronizer ring? I'll call somebody. No. Okay, purpose of the brass synchronizer ring. If you haven't caught it yet, it's the same as the transmission. We need to get this gear synchronized to the hub speed so that we can slide the sleeve over it. And now the sleeve would be click connected to the speed gear, which locks it to the hub, which locks to the input shaft. So if they're turning different speeds, that's why we need the synchronizer ring. You'll notice though, this one shows pretty good image of the back cut. You'll notice that. So here's sliding the back cut in. That's going to be kind of hard to get in, which is good because once it's in, it's going to be hard to pull this through. And that's why we don't have the pop out primarily. Cool. Pretty good. And then just keeping in mind, the gears generally are splash lubricated, but sometimes we use a pump with you know, a little screen to lubricate some stuff. This also talks about what type of lubricant. If it was depending on what model, it's generally going to be something like a 75/90 and 80/90. This is all gear lube. So this is more like what you'd put in a differential. And that kind of makes sense because it is a transaxle and it does have a differential. So a lot of the transmissions can use this too, but like some of the transmissions back in the day would use more like a thinner basic oil, whereas the transaxles would be using a gear lube because they have the differential in there. So it can vary. Also, this is no longer about transaxle specifically, but just generally. When we go to seal these, you're going to be looking at mostly not going to be a lot of gaskets. It's going to be like a RTV, FIPG type of thing. That makes it tough because a lot of times you got like the shafts and gears, you're trying to spline stuff, you're trying to bring the case together. When you're trying to set the case, it makes it even more difficult when you're dealing with like liquid RTV, like FIPG. FIPG, you know, you really want those cases to be set and the bolts to be in and at least tight within like 15 minutes. That's tough when you're trying to spline things together and shift shafts and rails and junk. So a lot of times what they'll go to is less of the RTV, more into what we call an anaerobic sealant. So ASE may ask about anaerobic sealant. An anaerobic sealant is a sealant that, look what it says, cures in the absence of air. What you think about that? What do you think that means? That means it's not like FIPG. You can apply it and you could leave it sitting there all day. Now, I wouldn't probably leave that. I don't know if I'd leave that all day, but you could. It won't actually cure. So does that take some of the stress off of you? You're like, oh yeah, let's put the right, you got to put the anaerobic sealant on the case, and then you got to assemble this. And don't even worry. It can sit there, chill. When did it start to cure though? What do you have to do to cure it? Does nobody know? What's it say? You have to actually bolt the case together, and then it's going to remove the oxygen. It's anaerobic. As soon as the oxygen is removed when the cases are together, then it'll cure. As long as it's exposed to the oxygen, it just sits there. It's pretty cool. So we'll use some anaerobic sealant on these transmission cases because it's really mostly going to help with, you know, making sure that we can spline everything and still have a good seal. Cool. So when we get into some of the diagnosis here and the service, I'd like to clarify a few things. Let's say, oh yeah, I want my transmission rebuilt. What do you mean by that? That's a kind of a hard thing to define. It's well defined in an automatic. In an automatic, that means you're going to get new clutches, new seals, new gaskets. You're going to clean the valve body. You're going to inspect all the hard parts. You're going to make sure all your measurements are in spec. That's exactly what an overhaul means. In a manual, it's like, does that mean you get all new bearings? Does that mean you get all new synchronizer rings? Does that mean you're getting sleeves? Or are we going to run the sleeves? Does it include speed gears? I don't really know. So it's not really a good term. I would say it'd be better to specify exactly what you did. An overhaul is very vague. So at a minimum, I would say if you said overhaul, that's going to be bearings. I don't know that it would really include synchronizer rings, and seals and gaskets, I guess. But with that being said, we don't typically request an overhaul for a transmission. You don't rebuild the transmission. If a transmission, it's a manual and it has an issue, you're probably just going to go in and fix the issue. Makes sense? So if it's grinding going into third, you're probably going to go in there and fix third, but also inspect it. And if that's it, that's it. Or if you had an input shaft bearing, you're probably going to be doing input shaft bearing. It's not real common to be like, oh yeah, we're going to go in and replace all sorts of stuff. You see what I'm saying? It's just kind of different. Cool. Here's some of the tools that you're going to use. Dial indicator, micrometer, maybe some various different seal installation tools, an inch pound dial type torque wrench. The press is a big one. So we're going to use a lot of press work. That's how the work looks. You might have to hang an engine to pull a transaxle. You might have bearing race drivers, maybe even some slide hammers and things. Bearing splitter is going to be common. Gear puller is going to be common. So these are the types of things we'll be doing. This one's a nice fixture, snap ring pliers, depth micrometers, maybe even some different types of pullers because they can be kind of difficult to pull some of these bearings, right? And again, when this is the note, if you buy a rebuild kit, that could mean a lot of different things, right? So it's not quite like it's not quite like an auto. Like here's a quote unquote rebuild kit. This one's actually a really nice rebuild kit. It's got all the bearings, all the seals, needle bearings, thrust washers, everything. But look, it also comes with the synchronizer rings. This would be this is called a major rebuild kit. So this is a nice one. But if you just go on, like I bought a Hyundai once and it had a horrible noise and I was going to fix the transaxle, I couldn't find a rebuild kit anywhere. If I went to the dealer, they'd sell me individual bearing and individual bearing and individual bearing. But I did find, I can't remember who made that transaxle, but I did find the company who made the transaxle sold a bearing kit. And that was the rebuild kit, just bearings, no synchronizer rings, no seals, no nothing. The problem was that bearing kit was like $500 or $600 just for the bearings. So I put a used transaxle in there for like $500, and that was it. It was done. So we don't really go in here the same as we do automatics. That's kind of the point. Now, when you prepare to do this work, you need to, it looks like a puzzle. It's something you can probably kind of figure out, but you're going to make mistakes. You need to really be following service information. So like this, we talked a lot about a T5 is an old manual that was pretty common back in the day. It was I think Tremec might have made it, 5-speed, might have been Borg Warner, whoever made it, I don't remember. But you know, you're just going to follow the steps, you know, say, pull this, remove this, separate it's not that different than an automatic, except it's a lot more simple, right? So here's some of the parts. Throughout the disassembly, we got to keep everything really nice and organized. So like later, you're going to see somebody flips this. So one of these was installed correctly and one of them installed backwards. And when we get into there, you're going to have to pull gears, right? You have to have the shaft out, then you have to have the shaft at the press, and you're going to use the bearing splitter to pull gears. If you put something on there wrong and you don't realize it till you're going to reinstall it, it can be a lot of work to separate and pull those gears back off. Cool. So even just pulling the shift tower, some of these I'm just going to skim through to get you understanding what our service is going to look like, because you're all going to do a front wheel drive and a rear wheel drive, right? You might have to do pin punch work. So if this has a roll pin, you got to take it out. This is a pin punch, not a Phillips screwdriver. The pin punch has a blunt end. It's going to successfully drive a roll pin out. It's not tapered, it's straight. Okay, so pin punch is going to be a thing. Vehicle speed sensors, reverse backup lamps, switches. You know, we got to disconnect some things like that. Other than that, there's nothing really electrical to this transmission. There's going to be maybe a couple electrical connectors, and that's it. Otherwise, it's all mechanical. This one is the speedometer gear drive. It's plastic. If you're servicing this, I'd replace that for sure. Here's that shift mechanism. So you can see you took out a bunch of bolts. Sometimes we'll have to smack it because the RTV or anaerobic sealant is kind of hardened up. But additionally, sometimes they tell you to put it in a specific gear. So you got to watch for that. And then here's like a bearing retainer we've slid out. We're about to slide that shaft out. It doesn't take much to get to this point. Then you're going to work that thing out of there. To get it out, sometimes you got to deal with snap rings. Snap ring pliers are going to be a must. You might even have to pull fifth gear. It's kind of common. You might have to pull a snap ring off, and sometimes you can slide it off. Other times there'll be holes, and you have to actually use a puller. But if it's a gear that's on the outside of the case attached to the shaft, you'll probably have to pull it to get the shaft out. That'd be pretty normal. This one, for example, has a tapered roller bearing right here, and this race makes it kind of nice because, like with an engine, if if that crankshaft spun that bearing, that would actually damage the block. Well, what's kind of nice with this, we use a big bearing race. So if we had a problem with this bearing, we're not real worried about the shaft or the case because the bearing rides on an inner race and the outside of the bearing rides on an outer race. So like the shaft and the case don't really get damaged on these. That's what's nice. So as long as we do a new bearing and the bearing comes with the races, we're good. We're not super worried. There's one ASE concept that they would ask about. A main shaft bearing journal was a little bit damaged. What should you do? It's like it's not a big deal. We're gonna put a race over that. Makes sense. The race is going to be the new friction surface. It doesn't have to have a perfect input shaft for the rollers because the rollers don't touch the input shaft. Cool. So there's a lot of that type of stuff. Sometimes it'll tell you put it in a certain gear. So like in this one, you got to put it in third and then tip it out. Now, this is specific for that T5, but once this is out, the work is drastically different. So you can see we're pulling the last few things off of this, including the counter shaft. And then if you're going to do the work, it's going to look like this. So let's just say there's a problem with, I think this is probably third. This is most likely first. If you got a problem with first and you need to get to first, you may very well need to pull. You're going to do a lot of work coming up here on the press. To start, actually, we need to pull the snap ring. Oh, this one, you're lucky. We got to pull from this side, so it's a little easier. Sometimes you pull from one side, sometimes from the other. Pulling that snap ring off. This snap ring is one-time use. Could you get away with it? Maybe. Could you re-squeeze it to tighten it up? Possibly. But per the manual, if you pull one of those snap rings off, you're supposed to put a new one on there. Okay, just so you know. And then when we want to pull that gear, you see we've got a bearing splitter right here. So we install the bearing splitter. You got to sort of like slide it under the gear. See how it's nice and flat and it's supporting that gear on like a good 10 plus teeth over here and 10 teeth over here. It can take that. You don't want to have it just barely catching the edge of the teeth. You'll chip the teeth. Makes sense. So that bearing splitter, we got to size it, kind of snug it up. You can tighten up the nuts and bolts and it'll hold it pretty well. And then you're literally just going to go ahead and press the shaft out from the center and you can see it's pulling it up. It's pulling the bearing as well. By the time you pull that bearing's junk. You really can't expect to pull a bearing and reuse a bearing. So once you go in there, you're getting bearings. That's why at a minimum, you're going to do bearings. If you do new bearings, but you're also really going for the speed gear down here, you can probably do that and get a speed gear and the bearings. But if you don't get the bearings, you're going to need those, right? Sometimes they have spiral snap rings. Here we're getting at this blocker ring right there. So let's just say this was the first gear blocker ring. If it was grinding going into first, all you do is you press it far enough apart to get to that blocker ring. And then you've accessed the blocker ring and you can put a new blocker ring in and then you're good to go. Cool. So it's not exactly rocket science, but you have to pay a lot of attention to which way things come apart. And we're going to disassemble, keep these keys in order, disassemble more. You're going to ultimately, when you get to the end, when you're pressing these, you're not going to want this main shaft to fall on the ground. You got to kind of catch it and disassemble, right? So remember I said a lot of your work is going to be on that main shaft on the press, looking at these individual parts. Cool. And then that's the main shaft right there. Then the counter shaft, it's kind of the same. snap rings, gear splitters, using a straight edge to check the case, using a feeler gauge to see if it's warped, right? Like simple stuff. Checking these bores to see if they're out of round or worn, which they don't really do. Checking the threads to see if they're clean. Looking at the case to see if you see any cracks or damage. Looking at your magnet, you know, the magnet will catch any of the larger debris. If there's debris on the magnet, you got to clean the magnet, right? Scraping it with a plastic scraper if it's an aluminum case, getting ready for new FIPG, pulling the old seals out. Here's a bushing, right? If you wanted to, that's an output, that's a bushing for the slip yoke. To change that bushing, got to press it out, inspect it, drive it in, drive the new seal in. Not exactly rocket science. The new seal right here, see this lip? That rubber lip is going to ride on a spinning shaft. Do you think that rubber lip should be clean and dry? We should probably lubricate that, right? So just not real complex things. If we put a new output shaft seal in and we put a little lubricant on that lip, the shaft is going to slide easier. It's going to be less likely to rip the rubber. A vent is a good one. Make sure the vent is not plugged. Anybody think they could guess if a vent was plugged, what you think the customer concern would be? Anybody know? Plugged up vent. Transmission fluid it gets hot, it expands, it gets hot, it expands. It needs to be able to push air out. If it can't push air out, it'll build a positive pressure. It could tend to push gaskets out. A clogged vent will cause multiple leaks. A clogged vent is similar to like a PCV valve that's not working. If you have various leaks on a transmission, check to make sure the vent's not clogged. Cool. So that's a good ASE concept. Right here, we actually have this is the release bearing collar and sleeve. So this is a little bit rough. We might be able to polish this or we might have to replace it. And that's because the release bearing has to slide across that. If this was a bearing that the race gets pressed onto the shaft, it wouldn't be a real big deal because the race stays in place. But the problem with the release bearing is it has to actually slide across that. So we need to clean that up, if not replace it. Also, sometimes there's a bearing race, or there's even sometimes shims in there. So one of the things you'll see, we're going to check end play. That's one of the ways we control the end play. Cool. So we're changing input shaft seal, not a big deal, but drive the new seal in, make sure it's lubricated. Here are shims. So this is a lot of times what it's going to take to set the correct preload on the bearings. Generally, we're reusing the same shims. Inspect this surface. So if this surface is scored or damaged, that seal's not going to seal. So a new seal is going to leak, just like the old seal leaked. Makes sense? If it's pitted or scored or, you know, seal type stuff, that would cause a leak. We're visually looking for broken teeth. These are the dog teeth. So these are the ones we'd want to look for, like the wear for the back cut, that back taper. These ones don't look worn, but if they did, we'd want to replace it. Because if we didn't and these were worn, can you guys remember what would happen if this back cut was worn? You got to know that. That'd be a pop out. That would pop out of gear if these teeth were worn. That's what that would do. Same if the teeth were worn on the sleeve, right? Checking the input shaft, making sure that's clean. Looking at not only the teeth, but also the cone surface. That can't be messed up because that's going to cause problems with the synchronizer ring. Looking right here, this is where the pilot bearing rides. Pilot bearing goes right on the end of that input shaft. Now we're talking about the output shaft and counter shaft. Again, we're looking at at all the gears at these bearings. We generally should already know if one of these bearings bad based on what type of noise it makes, but you also are going to inspect them. Again, this snap ring is used. That's a junk. Get a new one. Any snap ring and circlip and whatever, those are one-time use. Seals are one-time use. Washers, we want to check those, like this is a thrust washer. If it has excessive wear, we'd want to replace that. Making sure on those needle bearings or on those split needle bearings, we need to make sure this surface is really clean. If this surface was messed up, it needs a main shaft. If this surface is good, we're probably just going to do the bearing. Cool. Looking for cracking. And sometimes reverse gear has a brass bushing, so we're inspecting the brass bushing. And then obviously, when we do this transmission work, we're always going to replace gaskets and seals. We're going to do a lot of cleanup and prep. One of the things that you don't want to have is you go in and you fix that transmission for a grind, and then it comes back with a leak. Because if it comes back with a leak, remember, there's no transition pan typically. It's like you're going to probably have to pull the transmission out and split the cases again and clean it up and then reassemble it. So be very careful about, your FIPG or your anaerobic sealer and your gasket prep and making sure there's no oil running across the metal surface. And there's a lot of, it's not rocket science, but there's a lot of things that you have to make sure. And yes, Jimmy, I see you did say gear pop out. You got that right. Good job. There's a lot of stuff that we gotta make sure is good to actually be able to successfully fix one of these. Okay. Maybe not quite as much as what's going on in automatic, but it's still, there's some stuff. Cool. So that's sort of what this is going into. How to inspect the hub, the sleeve. Now you guys can see there's the hub, there's the sleeve, there's the keys, there's the synchronizer ring, and this one looks kind of smooth to me. This one's probably worn. See, those should have the nice sharp lines in there, and they don't. Checking the springs. Sometimes we'll lube those up with like a transmission assembly lube, petroleum jelly, getting the springs in place, getting the keys in place, getting the synchronizer rings in place, getting the sleeve over top of the hub while getting those keys in place can be a little tricky. But and then snap rings. I mean, this is what the work looks like. Checking the clearance between the synchronizer ring and the gear. That's going to show you if it's worn or not. But I probably would have done that on disassembly, right? So this is the oil pump. We don't do a lot with the oil pump, but you could take it apart and inspect it. There could be some tip measurements, tip clearance. You could lay a straight edge across it and do face clearance, but I don't think they're going to ask much on the ASE about oil pump. But if you want to know more about an oil pump, we did a lot for automatic transmission and a lot for engines, right? And sometimes they even have a little pressure regulator. Now, shift forks are interesting. There's a very important part right here. What I want you to remember is when you're driving, this sleeve is spinning. This fork, this rail is connected to your shifter, and this fork is connected to the rail. So if you think about this, ready? What if you were to leave your hand pushing kind of forward as you're in fifth gear? You're actually pushing this sleeve, you're pushing this rail rearward and this fork rearward against this sleeve. That's going to be kind of riding against this part of the sleeve. You can actually wear a fork down or wear a sleeve down if you're not careful about leaving your hand on the shifter with a lot of weight. Okay. So this one, for example, has got these plastic inserts, and that's to allow that sleeve to spin right across there. It's spinning, it's sliding across it, not wearing out the aluminum, not wearing out the sleeve. But if you do an overhaul, this is something that we should replace. Cool. Now here's what the ASE, the ASE would never accuse the driver of being a ding dong. What the ASE would say is you look at a sleeve and one side of the fork and one side of the sleeve are worn out. Like maybe this side of the fork is worn thin. What could cause that? A customer resting their arm on the shifter with a lot of force as they drive. But the ASE wouldn't say that. They would say a binding shift boot, some sort of shift linkage that's binding the linkage, pressing up against it. If you had an adjustment on the shifter cables on a transaxle and it was pushing on the shifter a lot, that would actually push this fork into the sleeve and it would wear one or the other or both. Kind of makes sense? That's something you definitely may see. There's your detent. spring and ball. There's roll pins. If you had to change an actual shift rail, a shift rail or a shift fork, you'd have to drive that roll pin out. Remember, that's with the pin punch. Inspecting the forks, inspecting and packing the bearings, installing a new needle bearing, installing spacers. So keep track of these spacers. If you were to not use this spacer, you'd end up with excessive end play. Just remember that. Cool. And again, a lot of this is similar. Now you're going to now you're basically reassembling. So we're reassembling the main shaft, reassembling, pressing, reassembling, sliding, pressing, reassembling. You're going to follow along with what service information says. But what I'm saying is you're going to be sitting over at that press, pressing stuff together and putting in snap rings and pressing stuff together. It's a very different work than an automatic. Right. But some of it's very delicate, making sure these keys are in place, making sure the springs are sitting down in there, making sure your speedometer gear goes on, making sure you have things lubricated, like where the bushing's going to go. It's not rocket science, but you got to be paying a lot of attention. Pressing bearings on. This is pressing a bearing on with the correct press. If you were to press a bearing with a press that's too big, it's going to ruin these rollers and the cage. You need to press. If the inner race is pressed onto the shaft, you need to press something that fits the inner race, not the outer race. Make sense? So like a lot of it's press knowledge. And it does actually have you press the shaft back into the case on this particular model. That may not always be the case. Did you see anywhere where someone was swinging a hammer and banging these things together? Sometimes for fun, I call the hammer the swing press, but in reality, no. Like these are meant to be installed with an installer or a press, not beat together, not bang and bang and bang, right? Then at the end, look what we do. Set the dial indicator on the input shaft, and we're going to move the input shaft up and down. If we forgot one of those thrust washers, what would this measurement be? What would that measurement be? Too high or too low? This would be too low right here. This would be too high. If you forgot a thrust washer, there's going to be too much play. You're going to have an end play measurement that's high. It's going to be excessive end play. Cool. So that's why we measure that, making sure everything is good. If it's not correct, by the way, you might actually get a different size shim. If it's too much play, you need a thicker shim. If it's insufficient clearance, you need a thinner shim. Cool. Not a big deal. And then sometimes they even have locking tabs and making sure this last few things are in. The main thing is getting that main shaft in and set right. And sometimes these bearings, need a certain amount of shims to get the correct preload. So like what I was saying right here, remember how we have those teeth that are cut at an angle, right? So remember some of the positives is they're quiet, they're still pretty strong. The negative is one shaft goes this way and one shaft goes that way. Well, what we'll need to do is we'll need to put a set of tapered roller bearings, and you can see how this one's facing out like this. We'd have another one facing the opposite direction. So that way, when this shaft tries to come this way, this tapered bearing being up against a race, it can withstand a lot of radial force, but it can also do a lot of axial force as well. However, to work, we need a set. We need one facing one direction and one facing the other. So on the other end of the shaft, there's going to be one facing the other way. And then the thing is, anytime, remember this, anytime you use tapered roller bearings, those need a bearing preload. It's not like a ball bearing where it's automatically just in place and it's done. We actually need to set a certain amount of tightness preload on that bearing. And that's why those shims are so critical too. That's going to set the correct amount of preload. If your preload is too tight, it burns the bearing up because it doesn't have enough space in there for lubricant. It has too much force on it and no lube. If it's too loose, that shaft is going to walk. It's going to move. If that shaft were to walk like this, A, that bearing is going to be destroyed because it's slopping all over the place. But B, think about that. If your shaft were to move, but your rails were to stay still, and your rail has the fork, and the fork catches the sleeve, but your shaft were to move, can't you see how excessive end play would cause pop outs? Excessive end play would cause it to pop out of gear too. That's part of why our rebuild includes that measurement. It's so critical. Cool. So a lot of good stuff. the bearing retainer. When we install the fifth gear, sometimes it slides on, sometimes you have to press it on. Sometimes the shaft is hollow and threaded, and you can use a bolt as an installer and pull it on there. A couple people got to see that yesterday. Cool. So that's overall new snap rings. I mean, this is pretty much the type of work you're doing. Then you're going to get your RTV or whatever it calls for, FIPG, RTV, uh, anaerobic sealant, whatever. And it's going to tell you how much at what size bead and how much time you got to work with it. And then you got to get it on, get it torqued, and then it won't leak, assuming you've done a good job at installing all your seals and etc. Right? So same type of thing. Cool. You can see the input shaft, output shaft. Now, this is the summary, all right? Because I threw a lot of stuff at you. A lot of stuff. But you have to know what symptoms would relate to what parts, right? So let's say oil leakage, simple, like faulty gasket, faulty sealant, faulty seal. But even further than that, if you had, let's say, an output shaft seal leak, it could be the seal, but it could also be the surface of the output shaft, remember? If you had an output shaft seal leaking and the drive shaft slip yoke would move because it was loose, a new seal is not going to fix that. That could be a worn extension housing bushing. The bushing needs to hold the shaft, and if the shaft is sloppy because the bushing is worn, that's going to leak, right? If it's overfilled, we don't worry about transmission pressure, but if it's overfilled, that could cause a leak. It could push it out the vent. Additionally, if you had leakage from, especially from multiple points, it could actually be a clogged vent too. Okay. Now, what if we had, and I don't see that wrong lubricant really causing oil leakage, but sure. What if we had hard to shift? If it's hard to shift in every gear, it sounds like that clutch is dragging. It's not disengaged all the way. If it's a front wheel drive, it could be actually control cable. So that'd be like literally, it'd be hard to move the shifter. Those shift cables can seize. It's like a parking brake cable. They could get rusty and get kind of stuck. Now, if it's hard to shift, what do you think about the faulty synchronizer assembly? Give me some feedback between a dragging clutch, a shift cable, and a faulty synchronizer assembly. What's the difference? Those could all cause hard to shift, but like they're different.
A dragging clutch would be in all the gears, and the synchronizer would only apply to whatever gears that synchronizer is for.
Exactly. You gotta understand that. If you've got, and we could go even a bit further, if you've got a hard shift in 1-2, that's when we bring in the shift rail because shift rail 1-2 is on one rail, right? If we had, it's hard to move forward and back in all of them, but it's easy to move side to side and it's a transaxle, I'd actually think the cable. If it was, let's say it was not hard to move, it would be not hard to move the shifter, but if every gear is tending to grind, that might more be like maybe the lubricant is too thick. Because if you think about it, all these gears are turning their own speed. If the lubricant's really thick and that synchronizer ring goes to equalize the speed, but it's like it's trying to speed it up or slow it down, but it's already churning and spiraling the fluid, it's going to make it harder for it to equalize the speed if the fluid's too thick. Okay, so improper lubricant can cause a hard shift as well, but it more means like probably not synchronizing, maybe tending to grind a little bit, maybe a little harder to get in gear. Okay, a lot of things with that. Cool. Now, if it won't shift at all, maybe it's the shift linkage, maybe it's the synchronizer, maybe it's, look at this, restricted travel of the fork. If a fork gets bent like this and you're trying to get first and it's like it can't reach first, it just won't get first. That could be a bent shift fork for sure. Cool. Now let's talk about jumps out of gear. Worn or damaged linkage. Remember the Collins story? Collins shifter's so sloppy that could make it pop out, jump out of gear. Interference with shift linkage, that would be like you grab first, but your boot, you got a big fancy shifter and this shift boot and whatever, but your boot is preventing it from going all the way to first. It might be like kind of in first, but it might tend to pop out. That could be a restriction there. Now look at this. This one's trippy. Broken or loose engine or transmission mounts. I want to pause on that. If you had a rear wheel drive and there was broken or loose transmission mounts, you know that you'd see your shifter moving all over, right? Like your whole transmission will move and your shifter will be like crazy. That could cause it possibly to jump out. But what if it's a front wheel drive? You wouldn't see that. But remember, the transaxle will be moving, but your body will be still. The cabin of the vehicle will be still, your shifter's still. So if your shifter's still, but your transaxle's moving, don't you see how that could maybe be pulling on the cables and stuff? That might actually cause it to pop out too. Cool. So there are sometimes some questions on the ASE where it's like, hey, a vehicle pops out of gear and it's a bad powertrain mount. Cool. And then I would say probably jumps out of gear, probably less a clutch pilot, but an input shaft bearing, yes, because that input shaft will move. And when it moves, the gears moves, but the sleeve would stay the same. And so the gear could move itself off of the sleeve and that would jump out. Similar with a shift fork, a worn synchronizer loosely, and this is what I want to clarify, not a synchronizer ring, a synchronizer component, such as the sleeve, such as the speed gear, dog teeth, these types of things, potentially. But we're mostly looking at worn dog teeth on the speed gear or worn back cut dog teeth on the sleeve. That's what we're really worried about right there. Cool. Going further, if we had a transmission locked in gear, maybe this thing has got shift linkage problem. More than likely, maybe it's more damaged, like maybe the rail won't move. Who knows? We might even have some kind of a problem where we end up with with it in two gears because we broke our interlock, and now you have the interlock pin dragging up against the shift rail. Won't really move. Cool clash. That's kind of like a hard shift, but it's a little more specific. It's like you hear it, right? A lot of times, if the gears are clashing, they're also kind of hard to move. So we talked about that, I think, enough. If it's all gears, clutch drag. If it's certain gears, maybe a damaged shift fork. If it's certain gears, maybe a synchronizer ring. Most likely, actually. The synchronizer rings made of brass. It wears. It just is what it is. We can expect that. We can anticipate that. Okay, now it's my tribute. Noisy in neutral. Interesting. In neutral, got to think of what's spinning. If you are neutral and you let the clutch out, the input shaft spins, the counter shaft spins, the output shaft doesn't spin. Okay. So worn oil level, that would cause probably a noise, but ultimately probably the bearings are bad by then. Input shaft, counter shaft, yes. Output shaft, no, no. An output shaft is only when moving. That goes with vehicle speed. Cool. Noisy in one gear. Well, the thing is, if you're in third, you're transmitting torque through the third gear, speed gear, and countershaft gear. So if there's a broken tooth, it'll probably be more noisy in third. All right, but what about if it's noisy in all the gears except it's quiet in third? Then it would be that needle bearing. Okay, that third gear needle bearing, split needle bearing. Cool. And then depending on all gears, it could depend on a number of different things. I feel like this is really good. I feel like I would go a little bit more in detail with what shaft turns and what shaft doesn't turn. So again, if it's noisy in all gears except for fourth, what are your thoughts? Remember this? Fourth gear is quiet. Remember, it doesn't transmit torque through the counter shaft in fourth. The input locks to the output in fourth. Makes sense? These are the types of things that I see on the ASE regularly. But generally, like this says, if you have a hard to shift, check for clutch pedal free play, check for air in the lines, check the clutch disc. And then if it's okay, unfortunately, then you're into the transmission transaxle, right? But we check the externals first. Don't yank a transmission or transaxle out if you didn't check the clutch play, the clutch pedal free play. If you didn't check to see if there's air in the clutch cylinder, in the clutch release system. Make sense? Cool. And then similar, if it's pop out, if you're already in the transaxle, you're going to check various things inside the transaxle. I'd probably check your shift linkage first, of course. And then this is talking about if we have thrust, you can actually measure with a feeler gauge when we're trying to move it. Sometimes they do have specs to make sure there's a certain amount of clearance right there. And then checking the shift fork. So if we had this detent ball missing, 1-2 would be sloppy. Remember that. If we had a problem with this ball and spring and whatever was messed up and it was binding, 1-2 would be, it would be hard to move, right? So just visualizing these shift rails and these sleeves and just kind of, if they ask a question, be able to picture how it moves, what forces are on it, these types of things. Like right here, we have a bushing. If we had a bad bushing, that shifter would probably be pretty sloppy. It might also have a hard time getting all the way over to 1-2 or all the way over to fifth and reverse or fifth and sixth. Cool. And then probably the thing I want to just make sure you understand is with pop out of one gear, you're looking at back cut problem, more than likely. Makes sense? If it's something to do with the rail, if it's popping out, if it's an issue with the ball and the spring, that's going to affect 1-2 or 3-4. But if it's just popping out of first, that's why I told you the story about my plow truck. If it's just popping out of first, that's probably more like the back cut on the sleeve or the back cut on the speed gear dog teeth. Okay. Feel like you're decent? There was a lot of stuff to cover. I tried to cover as much as I could quickly and highlighting the important points. You guys got any questions? Hit me. What you got?